Space is not just empty darkness. It has layers, depth, and scale that grows more extreme the farther you go. Every step away from Earth pulls you into something bigger, colder, and harder to understand. But how far does it really go, and what waits at each level? Let's dive into the 12 levels of deep space, moving outward until distance, time, and size start to break down. Level 1. Near-Earth space. Imagine blasting off from Earth. The ground drops away, the roar of engines fades into the thin, cold vacuum, and suddenly the sky turns black, dotted with stars. Below, the planet you know, the blue oceans, white clouds, sprawling continents, shrinks fast. You're not just leaving Earth, you're entering low Earth orbit, the first frontier of space. From roughly 160 kilometers to 2,000 kilometers above the surface, this is where humanity first steps out into the unknown, where the familiar rules of life start bending. And it's not just about floating, it's about survival, science, and danger hidden in plain sight. Near-Earth space is crowded, alive, and unforgiving. Thousands of satellites, from communication relays to spy platforms, orbit silently, like invisible sentinels. And humans, a handful have called this region home for months at a time, aboard orbital stations. The very first steps here were small, mechanical, and cautious, but they set the stage for everything that came after. Low Earth orbit, or LEO, may sound close, but in reality, it's the beginning of the extreme. At 160 to 2,000 kilometers above Earth, you're high enough to see the curvature of the planet, yet low enough to feel Earth's pull just enough to keep moving fast in orbit. Objects don't fall, they float. Water forms balls. Pens hover mid-air. Even your own movements have to be carefully controlled because in microgravity, a tiny push sends you spinning or drifting across the cabin. Microgravity is more than just a cool trick for astronauts. It changes everything about life. The human body evolved under 1 g of force, constantly pushing down on muscles, bones, and fluids. Take that away even partially and things get strange fast. Muscles weaken. Bones slowly lose density. Fluids shift to your upper body and head, giving astronauts puffy faces and even affecting their eyesight. Every experiment aboard the ISS or other orbital stations is influenced by this invisible force, or lack of it. The behavior of fluids and air becomes unpredictable, and even fire acts strangely. Flames form spheres and drift instead of rising. Combustion can be uneven and dangerous, making fire safety a constant concern. Living in LEO isn't like camping at high altitude. It's an entirely alien environment that humans have learned to navigate with a combination of science, engineering, and sheer trial and error. And while the view is breathtaking, the planet spinning below, sun rises every 45 minutes, the danger is never far away. Cosmic rays, energetic particles that come from exploding stars and distant galaxies, stream through LEO. Earth's magnetic field protects the planet's surface. But here, radiation can damage cells and electronics. The Van Allen belts, 2 donut-shaped rings of trapped particles around Earth, add another layer of risk. Spacecraft must carefully navigate them to avoid long-term exposure, and astronauts rely on shielding and planning to survive. Every orbit carries invisible hazards that make LEO both fascinating and deadly. The journey into near-Earth space didn't happen overnight. It began in 1957, when Sputnik 1, a small beeping metal ball, was launched by the Soviet Union. Simple and crude by today's standards, it changed the world. Humanity had left the atmosphere. Space was no longer a dream, it was reachable. After Sputnik came a rapid escalation. The United States responded with Mercury and Gemini missions, putting humans into orbit for the first time. Short flights turned into longer missions, testing how humans could live and work in microgravity. Every orbit, every experiment revealed a new challenge. Muscles weakened, bones changed, fluids redistributed, sleep patterns disrupted. Each problem had to be solved in real time, with no backup from Earth other than radio instructions. Then came the first orbital stations. Skylab in the 1970s was humanity's first serious attempt to create a home in space. Crews lived for weeks and months, conducting experiments on microgravity, solar radiation, and material science. It was a prototype, a laboratory suspended above Earth, teaching lessons that would be essential for long-term survival in orbit. By the 1990s, international collaboration redefined what was possible. The International Space Station, ISS, launched in modules starting in 1998, became the crown jewel of near-Earth habitation. Spanning the size of a football field, rotating around the planet every 90 minutes, it became a floating city in space. Astronauts experience 16 sunrises and sunsets every single day, all while running experiments, maintaining life support systems, exercising to counter bone and muscle loss, and communicating with Earth. The ISS isn't just a laboratory. It's proof that humans can survive, work, and thrive in orbit for years at a time. Meanwhile, other nations carve their own paths. China's Tiangong stations have created a parallel presence in LEO, showing that space is no longer the domain of a single power. Tiangong hosts scientific experiments, tests new technologies, and supports extended crew stays, further proving the feasibility of life in orbit. These modular stations can expand, change, and adapt to new missions, highlighting how adaptable human ingenuity can be in the harshest environments. The last decade brought private companies into the mix. SpaceX, Blue Origin, and others are changing the rules. Reusable rockets have turned space from an expensive government-only venture into a growing commercial playground. SpaceX's Crew Dragon ferries humans to the ISS, proving that private enterprise can operate safely in orbit. Soon, commercial space stations may host tourists, researchers, and entirely new industries. Humanity is no longer just visiting near-Earth space. We are starting to inhabit it. Even with the incredible technology and milestones, near-Earth space remains hostile. Microgravity, radiation, and extreme temperatures test every system and every human. Astronauts must exercise for hours a day just to prevent muscles from wasting. They must monitor bone density, blood pressure, and eye health constantly. Every meal is carefully planned. Every movement is considered. Living here is a balancing act between maintaining the body, running experiments, and staying alive in a place where a single malfunction can be catastrophic. Radiation is a constant threat. Cosmic rays and solar particles strike the spacecraft and its occupants continuously. While shielding can reduce exposure, solar flares and coronal mass ejections can deliver sudden bursts of dangerous radiation, forcing crews into reinforced shelters. Electronics and communication systems are also vulnerable. A single surge can disable equipment or alter mission outcomes. In orbit, every day is a test of human resilience and engineering precision. The environment is extreme in other ways too. Temperatures in LEO swing dramatically. Sunlight can heat surfaces to hundreds of degrees Celsius, while shaded areas plunge close to absolute zero. Materials must expand and contract without cracking. Fuels must be carefully stored, and air and water must be recycled flawlessly. Mistakes are unforgiving. Even small debris, tiny flecks of paint or old satellite parts moving at thousands of kilometers per hour, can punch holes in spacecraft. Near-Earth space may seem close, but it is perilous and unrelenting. Despite all of this, life persists. Astronauts float, work, sleep, eat, and experiment. Satellites orbit silently. New modules are added, rockets continue to launch, and each mission pushes the limits further. Near-Earth space is humanity's first real foothold beyond the planet. It is both home and trial, a place where science, courage, and technology meet. Every orbit teaches new lessons, uncovers new hazards, and proves that humans can exist in a world without gravity, air, or the warmth of the sun filtered through the atmosphere. Beyond this fragile skin of air is a universe that doesn't bend to human needs, a place where survival depends entirely on careful preparation, technology, and constant attention. In this realm, the ordinary rules of life dissolve, and every moment is a negotiation with the laws of physics. Challenges of near-Earth space. Humans in orbit live in a constant play with this invisible environment. Even breathing becomes a carefully monitored activity. Air must be filtered, oxygen levels maintained precisely, carbon dioxide removed before it reaches dangerous levels. Humidity, temperature, even the slightest shift in pressure can become life-threatening if neglected. Water, something taken for granted on Earth, is a precious resource. It is recycled, purified, and rationed. Every sip, every droplet, moves through a closed system, transformed and reused again and again. The precision required for daily survival is staggering. Food in orbit takes on an entirely new role. Without gravity, liquids float and crumbs drift, creating hazards. Engineers and nutritionists design meals that can be eaten safely in microgravity while still providing the calories, vitamins, and minerals necessary to maintain muscle mass and energy. Astronauts live on specially prepared foods, often dehydrated, packaged, and carefully managed. Cooking as we know it disappears. Everything must be controlled and contained, yet the goal remains the same. Keep humans functioning at peak capacity despite living hundreds of kilometers above the surface. Sleep too becomes a challenge. In orbit, a day lasts 90 minutes, with 16 sunrises and sunsets. The body's internal clock struggles against the constant rotation of the planet below. Astronauts use sleep masks, controlled lighting, and carefully timed schedules to trick their minds into resting, but every cycle feels different. Even this seemingly mundane task is a test of adaptation. Every habit, every routine, has to be recalibrated for life without gravity. Communication is another lifeline. Radio waves carry conversations, instructions, and data between spacecraft and mission control on Earth, bridging hundreds of kilometers in seconds. The tiniest delay can complicate maneuvers, and maintaining contact is essential for safety, for navigation, and for the mental well-being of the crew. Isolation is real. The view may be spectacular, but humans in orbit are separated from the familiar world by an invisible wall, with only the signals of computers and distant voices linking them to the life they left behind. Then there's the thrill of exploration itself. Every window on an orbital station frames a constantly changing view. The sun rises in a flash of orange and pink. Earth's weather systems swirl below, and cities spark like strings of fire at night. Satellites pass silently across the sky, sometimes close enough to be glimpsed with the naked eye, tracing paths in perfect precision. The planet rotates beneath in a never-ending ballet, while above, humanity tests its limits. The human presence in low Earth orbit has evolved rapidly in recent years. Private companies now push beyond what governments alone once achieved. SpaceX has shown that rockets can return safely, reuse their components, and deliver both humans and cargo to orbit reliably. Plans for private space stations are already underway, signaling that LEO is no longer just a proving ground for astronauts. It's becoming a destination in itself. Scientists, engineers, and even tourists may soon live and work in orbit without being part of a government mission. The stakes are high, but so is the ambition. And life in orbit continues to teach lessons that are critical for the future. Engineers develop new materials to withstand radiation, experiments test how plants grow without gravity, and researchers study how the human body adapts to a life that Earth never intended for it. Every experiment is a window into the possibilities and limits of human endurance. Every mission is a story of survival, adaptation, and discovery. Beyond the physical challenges, there's a psychological dimension to life in near-Earth space. Being surrounded by the blackness of space, suspended above everything familiar, can weigh on the mind. Isolation, confinement, and the awareness of extreme danger require mental resilience. Astronauts must remain alert, disciplined, and emotionally balanced while performing delicate tasks that leave no margin for error. Yet these challenges have pushed humans to achieve remarkable levels of focus, cooperation, and creativity. In orbit, human ingenuity is tested alongside technology, and sometimes it is ingenuity that keeps life alive. The technology is staggering. Life support systems operate continuously, monitoring oxygen, pressure, temperature, and waste. Solar arrays stretch outward to harvest sunlight, powering everything from computers to water filtration systems. Robotics assist with maintenance and experiments, extending human reach beyond the station's physical limits. In every module, every corridor, and every instrument, decades of research and trial-and-error design converge, creating a floating ecosystem capable of supporting life in one of the harshest environments imaginable. Near-Earth space is not static. Every orbit, the station moves at nearly 28,000 kilometers per hour, circling the planet once every 90 minutes. Satellites whiz past, some old, some new, forming a network of machines that hum silently in the void. Space debris, tiny remnants of past missions, drifts at lethal speeds requiring constant vigilance. Even the simplest maneuver, like adjusting the station's orientation, requires precision and planning. In orbit, the smallest miscalculation can have catastrophic consequences. The sense of scale is huge. Looking down, Earth is immense, yet fragile. The blue atmosphere is a thin layer protecting life from the void beyond. Up here, humans live on the edge of survival, caught between the familiar gravity of the planet and the endless expanse of space. The contrast sharpens every sensation: light, sound, motion, even the passage of time. Each orbit is both a scientific mission and an intense human experience. Private missions and commercial plans promise to make this level of space more accessible. Companies are developing orbital hotels, research hubs, and even manufacturing facilities. These new ventures aim to exploit microgravity for materials and medicines, while creating experiences for people who have never left the surface. What was once the exclusive domain of government astronauts is becoming a broader frontier, blending exploration with enterprise. Yet every advancement comes with risk. Life in near-Earth space remains dangerous. Radiation, microgravity, and the unpredictability of the environment are constant. The technological marvels that allow survival are fragile. Astronauts depend on them continuously, understanding that failure in orbit is unforgiving. Every launch, every docking, every experiment carries stakes higher than anything on Earth. And still, humans continue to push upward, orbiting, experimenting, and adapting. Low Earth orbit is more than just the first step beyond our atmosphere. It is a laboratory, a proving ground, a place where humans learn the rules of a universe that doesn't bend to our needs. Every day in orbit is a blend of science, discipline, and awe. The lessons learned here will carry humanity further toward the next levels of deep space, where the challenges and the wonders grow exponentially. And as the station continues its silent orbit, the planet below spins endlessly, oceans glinting, clouds swirling, cities sparkling like tiny circuits. Above, the sky stretches black and infinite. Humanity floats between, suspended, learning and daring, while the edge of space keeps widening just beyond the reach of even our most advanced technology. Near-Earth space is alive. It is dynamic, dangerous, and endlessly fascinating. It is the first home humans have built beyond Earth, and the first taste of what lies beyond our planet. Every orbit is an adventure, every experiment a discovery, and every sunrise a reminder that we are no longer confined to the ground. The first level of deep space is not just a place, it is the proving ground for everything that will come next. Level 2, Geosynchronous orbit, and the near-solar neighborhood. After months floating above the planet in low Earth orbit, the next stage of the journey begins. The engines fire again, pushing the spacecraft higher, farther from Earth's surface. Gravity is still present, but its grip loosens even more. Below, the blue and white marble shrinks fast, clouds swirling, continents flattening. The atmosphere fades into a thin veil, and the sun, once enormous in the sky, now seems smaller, distant, and sharper. This is the threshold of geosynchronous orbit, around 35,786 kilometers above Earth. It's no longer a place for human life yet. Instead, it is the realm of technology, of satellites that hold together modern civilization, of signals that travel invisibly, connecting billions of people across the globe. Here, satellites appear almost frozen relative to the Earth below. Unlike low Earth orbit, where objects circle the planet every 90 minutes, A geosynchronous satellite rotates at the same speed as the Earth itself. From the ground, it seems motionless in the sky, hovering over the same location at all times. These silent sentinels are vital to our daily lives, though few realize it. Every phone call, every GPS direction, every weather map on your screen, every television broadcast relies on these orbiting machines. Telecommunications satellites are the most visible in geosynchronous orbit. They transmit signals for television, internet, and phone networks. Data streams pass invisibly through these satellites every second, hopping from one device to another, then back to Earth. Weather satellites constantly scan the planet, monitoring hurricanes, storms, and heat waves, predicting events days before they happen. Without them, modern civilization would be blind to the movements of the atmosphere, blind to the signals that keep billions of people connected, and blind to the invisible traffic that speeds across the globe in microseconds. GPS satellites are another essential component. Orbiting in precise paths, they provide exact location data to millions of devices, from smartphones to shipping vessels, airplanes, and military operations. They rely on extremely accurate clocks, atomic-level precision, and constant calibration. Without them, navigation would be chaotic. Cities, highways, and the globe's logistics network would grind to a halt. From a spacecraft above, it is possible to imagine the invisible lattice of signals weaving the planet together, connecting one city to the next, silently orchestrated by machines floating in near-perfect synchrony above. Yet this orbital zone comes with challenges. The higher you go, the more crowded it becomes. Space debris is no longer confined to low Earth orbit. Old satellites, spent rocket stages, and fragments from collisions float at immense speeds, sometimes exceeding 10 kilometers per second. A small piece of debris can destroy a satellite or shatter it into hundreds of fragments, creating more hazards in a chain reaction. Engineers must calculate trajectories carefully, predict collisions, and occasionally maneuver satellites to avoid impact. Every launch adds more objects, each a potential risk for the delicate web of technology orbiting our planet. Mega constellations have changed the dynamics dramatically. Companies like SpaceX have begun deploying thousands of small satellites in coordinated orbits to provide global internet coverage. Starlink, for instance, has already launched over 4,000 satellites, with plans to reach tens of thousands. While their goal is connectivity, the sheer scale adds risk. Satellites must avoid each other, avoid debris, and maintain constant coordination. Imagine thousands of tiny objects moving silently at incredible speeds in a narrow band around the planet. The potential for collisions is real, and tracking them requires an army of sensors and a network of calculations, all running continuously. From geosynchronous orbit, the Sun appears smaller but brighter, a concentrated sphere that bathes the Earth in light from hundreds of thousands of kilometers away. Shadows become sharper, and the planet below is bathed in a softer light, clouds casting long shapes across deserts and oceans. The curve of the Earth is pronounced. The horizon bends away. Distant mountains flatten into the landscape of the planet as it spins beneath. Below, the cities appear as tiny clusters of lights, faint yet steady, while highways trace silver paths connecting them, like threads. Floating here, it is possible to feel both the fragility and the precision of human civilization, maintained by machines that never rest, always orbiting, always moving with mathematical precision. Beyond the mechanical and technological marvels, the journey continues outward. Leaving geosynchronous orbit behind, the spacecraft passes through a transitional region where Earth's gravity is weaker but still felt, and the Sun, now distant, dominates the sky. For the first time, the familiar constellations begin to shift subtly. Earth becomes smaller, a blue and white marble drifting in blackness, and the neighborhood of stars beyond the Sun comes into focus. The closest stars appear as faint, unwavering points of light. Proxima Centauri, a red dwarf, shines dimly but persistently. Only 4.24 light-years away, it is the nearest star beyond the Sun, yet even at this distance, it would take centuries to reach with current technology. In 2016, astronomers discovered Proxima b, an exoplanet orbiting in its star's habitable zone. Though orbiting a dim, volatile star, the planet raises questions about life beyond Earth. Conditions may not be ideal, but its presence reminds humanity that planets orbit other suns, worlds waiting to be explored in ways we can only imagine. Nearby, Barnard's star, a fast-moving red dwarf 6 light-years away, threads its way across the sky. It may not have planets as promising as Proxima b, but it highlights the density of our stellar neighborhood. Stars, once thought to be isolated, are now mapped in incredible detail. Every point of light in the near-solar neighborhood represents potential worlds, planets, and moons, some already discovered, others waiting to be found. Then there is TRAPPIST-1, a system of 7 Earth-sized planets orbiting a faint, cool dwarf star 39 light-years away. 3 of these planets sit in the star's habitable zone, where liquid water could exist. This discovery, one of the most exciting of recent decades, revealed that small, cool stars could host planetary systems with worlds that may be Earth-like in size and composition. Observing them from a spacecraft beyond geosynchronous orbit, it is possible to imagine what it would take to travel there, how long the journey would be, and what life might look like on these distant planets. But even as the imagination wanders, the challenges are immense. Distances in the solar neighborhood are enormous. Even the closest stars are years away at the speed of light. Sending probes, let alone humans, requires technologies still beyond current capabilities. Yet the observations alone have transformed human understanding of the universe. Every new exoplanet discovered adds a dot on the cosmic map, reshaping assumptions about how common Earth-like worlds are and what conditions life might need to survive elsewhere. Returning to Earth for a moment, the perspective from this height is unlike anything seen from the surface. Geosynchronous orbit is far enough that Earth's curvature dominates the view. The Sun appears almost static, hanging in the sky for hours at a time, casting its energy steadily onto solar arrays and satellites. The faint glimmer of cities at night is visible. Electricity moving invisibly, signals transmitted, a web of human life maintained by machines orbiting silently above. At this height, every system, every orbit, every satellite becomes part of a massive complex structure, sustaining communication, navigation, and observation across the planet. From this vantage point, space feels like both a frontier and a neighborhood. Satellites are clustered in predictable patterns, yet invisible forces, solar winds, radiation, and gravity push and pull on them constantly. Collisions, though rare, have consequences that ripple through the network of orbits. Engineers on Earth monitor each satellite continuously, making minute adjustments to keep them on track. Every satellite maneuver is calculated with extreme precision, because even a tiny misalignment at this distance can cause problems across the system. The sheer number of satellites is remarkable. Older satellites remain in orbit for decades after their missions end. Some move to graveyard orbits farther away to reduce collision risk, others drifting uncontrolled. Even tiny fragments of debris travel at thousands of kilometers per hour, capable of damaging functioning satellites. As more private companies launch satellites for communication, observation, or research, this invisible traffic jam continues to grow, and every launch is a careful negotiation with physics, technology, and risk. Beyond technology, this is also a region of observation. Telescopes in orbit, stationed beyond the interference of Earth's atmosphere, provide unparalleled views of the universe. Geosynchronous orbit is not as high as Hubble or James Webb, but it allows stable, uninterrupted observation over specific points on the planet or the sky. Instruments here track storms, monitor environmental changes, and even assist in detecting objects approaching Earth, such as asteroids or comets. From this orbit, the universe beyond begins to come into view. Stepping even further into the solar neighborhood, the spacecraft drifts past Earth's geosynchronous satellites, past the edges of Earth's magnetic influence, and into a quieter region where the nearest stars begin to dominate the view. The Sun, still visible, appears smaller and more defined. Light from distant stars is now detectable without interference from Earth's atmosphere. Red dwarfs, yellow dwarfs, and faint planetary systems fill the darkness. Even with advanced telescopes, the proximity of these stars makes it possible to study them in unprecedented detail. It's possible to visualize what these worlds might look like up close. Proxima b, orbiting a star smaller and cooler than the Sun, could have surface temperatures that allow liquid water under the right conditions. TRAPPIST-1's planets, tightly packed, may be tidally locked, their days and nights unlike anything on Earth. Barnard's star may have small, rocky worlds, cold and dimly lit. These stars, each a neighbor in cosmic terms, hint at countless possibilities, worlds forming and orbiting in ways both familiar and alien. Even though this stage of space is dominated by technology, the human imagination cannot be contained. Each satellite orbit, each observation, and each discovery brings humanity closer to understanding the vast expanse just beyond the Sun. Geosynchronous orbit links our planet with the stars beyond, maintaining the invisible infrastructure that keeps Earth connected, while opening a window onto the near-solar neighborhood. The view from this height combines the precision of engineering with the vast possibilities of exploration, showing both the fragility of civilization and the vastness of the universe beyond. Level 3. The asteroid belt and the inner solar system frontier. Look out the window and the stars are no longer distant pinpricks. They're signs of things waiting to be explored. Ahead, beyond the orbit of Mars, the quiet of space breaks into chaos. A belt of rocks stretches for hundreds of millions of kilometers, swirling around the Sun, each fragment a world of its own. This is the main asteroid belt, a region both dangerous and full of opportunity, a frontier of the inner solar system that humanity is only beginning to understand. Unlike the neat orbits of planets, the asteroid belt is crowded, chaotic, and endlessly varied. Tiny meteoroids drift silently past massive bodies hundreds of kilometers wide. Each one is a relic from the early solar system, a fragment of the building blocks that never coalesced into a planet. They are made of rock, metal, and sometimes ice. Their surfaces are scarred by collisions stretching back billions of years, pitted like the skin of some ancient giant. And yet, these seemingly random fragments are not just space debris. They are a record of the Sun's formation and the evolution of the planets, a time capsule floating in orbit around the star that powers the solar system. Among these countless bodies, a few stand out. Ceres, the largest object in the belt, is classified as a dwarf planet. At nearly 1,000 kilometers across, it dominates its neighborhood. NASA's Dawn mission revealed it to be icy, with signs of past water activity, possible cryovolcanoes, and mysterious bright spots that hint at salt deposits. Vesta, another large body, is less icy but still remarkable. A rocky world with massive craters and cliffs taller than anything on Earth. These worlds are more than curiosities. They are laboratories in space, frozen records of chemical processes that shaped the early solar system. Every year, new small objects are discovered. Meteoroids, some just a few meters across, cross paths with larger asteroids, creating showers of debris that occasionally fall to Earth. Some are harmless fireballs burning in the atmosphere. Others, like the Chelyabinsk meteor of 2013, explode with enough energy to damage buildings and injure hundreds. Understanding the paths of these objects is not just academic. It is essential for planetary defense. Tracking them, modeling their trajectories, and predicting potential collisions is now a high-priority science. Exploration of the asteroid belt has ramped up dramatically in recent decades. NASA's Dawn spacecraft, launched in 2007, provided an unprecedented look at Ceres and Vesta, mapping their surfaces, analyzing their compositions, and revealing the complexity of these distant worlds. Dawn's data transformed our understanding of the asteroid belt, showing that these bodies were not static, but dynamic, with histories shaped by collisions, ice, and even water-related processes. Other missions took a different approach. OSIRIS-REx, launched in 2016, traveled to the near-Earth asteroid Bennu to collect samples for return to Earth. The spacecraft studied Bennu's surface, analyzing its composition and mapping it in stunning detail before carefully retrieving a capsule of pristine material from a world untouched by humans. Meanwhile, Japan's Hayabusa 2 visited the asteroid Ryugu, collecting surface and subsurface samples, revealing carbon-rich materials and minerals that could shed light on the origins of life on Earth. These missions show that asteroids are not just dangerous rocks, they are scientific goldmines, holding clues about chemistry, water, and possibly even the precursors to life. But the asteroid belt is not just about science. The same objects that can teach us about the early solar system are also resources waiting to be tapped. Asteroid mining is no longer just science fiction. Certain asteroids are rich in metals like nickel, iron, and platinum, along with water that could be broken down into oxygen and hydrogen for fuel in space. Companies and space agencies are already planning missions to tap into these resources. Water extracted from asteroids could fuel deep space exploration, refueling spacecraft without the need to return to Earth. Metal-rich asteroids could supply materials for in-space construction, reducing the need to launch everything from Earth's gravity well. The potential is staggering. Even a small asteroid could contain metals worth billions of dollars if returned to Earth. Though the challenges of extraction and transport are immense, microgravity, radiation, and the sheer distance make mining in space difficult, but progress is being made. Robotics, autonomous mining equipment, and spacecraft capable of long-duration operations are under development. These missions may transform the way humanity expands into the solar system, turning the asteroid belt into a hub of activity, not just for observation, but for industry. Every asteroid in this belt tells a story. Collisions have broken some into thousands of fragments. Some have moons of their own, tiny bodies orbiting them in silent companionship. Others spin unpredictably, their rotation chaotic, shaped by centuries of solar radiation and impacts. Scientists study them not just for potential resources, but to understand physics in extreme conditions. How does a body with no atmosphere, tiny gravity, and constant bombardment survive over billions of years? What happens when two asteroids collide at speeds faster than bullets? These questions guide every mission, every observation, and every model built to predict the belt's behavior. The asteroid belt is also a crossroads for humanity's ambitions in the inner solar system. Spacecraft traveling to Jupiter or beyond must pass through this region, navigating between countless rocks. Every journey is a negotiation with gravity and momentum. Engineers plan trajectories carefully to avoid collisions while taking advantage of the belt's influence on orbital paths. Even spacecraft like Dawn, OSIRIS-REx, and Hayabusa 2 use the asteroids themselves to test technologies for maneuvering, navigation, and remote operations. Beyond the major bodies and potential resources, countless smaller fragments drift, some so small they are invisible to telescopes. These meteoroids, moving at tens of kilometers per second, represent both risk and opportunity. While they could damage spacecraft, they also offer a way to study the raw materials of the solar system without landing on a larger body. Collecting these particles, analyzing their composition, and understanding their origin provides insights into processes that occurred billions of years ago, long before the planets themselves stabilized into the orbits we now know. Asteroid missions have revealed surprises. Some bodies are more like rubble piles than solid rocks, held together loosely by gravity. Others show evidence of water ice beneath their surfaces. Some carry organic compounds, the raw materials of life, preserved in cold, dark environments for billions of years. Each discovery adds a layer to our understanding, revealing a solar system more dynamic and complex than anyone imagined just decades ago. The potential benefits of asteroid exploration are immense. Water, metals, and organic compounds could support long-term missions to Mars, the moons of Jupiter, and beyond. Mining could support habitats, fuel spacecraft, and provide raw materials for structures in orbit or on distant worlds. Scientific knowledge could accelerate human expansion into space, giving us the tools to live off the Earth rather than carrying everything from the surface. At the same time, the asteroid belt remains a dangerous frontier. tiny errors in navigation could result in collisions. Microgravity conditions complicate mining or landing. Radiation from the sun and cosmic rays permeates every kilometer of space. Spacecraft must be engineered to withstand extreme temperatures, impacts, and prolonged isolation from Earth. Humans venturing into this region must be prepared for months or even years of travel, far from the safety and support of the planet. Even as these challenges loom, the allure of the asteroid belt is irresistible. It is a region of untapped potential, a laboratory for science, and a proving ground for technology that will eventually take humanity deeper into the solar system. Every mission that ventures here, every asteroid studied or sampled, brings new knowledge and new possibilities. The future of the asteroid belt may include permanent outposts, robotic mining stations, and spacecraft continuously ferrying resources back to Earth orbit or to other planets. Advances in propulsion, robotics, and life support will make extended missions possible. As technology improves, the asteroid belt could transform from a remote frontier into a bustling region of activity, bridging the inner planets and enabling the next phase of human expansion into the solar system. Even the smallest discoveries matter. Tiny asteroids, previously invisible, are now tracked by advanced telescopes. Their trajectories are monitored for potential collisions with Earth, and their compositions are analyzed remotely. Each fragment carries clues about conditions billions of years ago, before the planets formed, before life emerged on Earth. The asteroid belt is both a threat and a treasure trove, a place where science, industry, and human curiosity intersect in ways never seen before. Gravitational dynamics and solar radiation. Out here in geosynchronous orbit, gravity is still very real, even if it doesn't feel like it. The satellites hovering above Earth appear perfectly still to someone on the ground, but in reality, they are constantly negotiating a web of invisible forces. Earth's gravity is the anchor, pulling everything toward its center, keeping the satellites in orbit. But this pull isn't simple or uniform. Earth isn't a perfect sphere. Its equator bulges slightly. Mountains, oceans, and mass variations create subtle differences in gravitational pull. These irregularities, called the geoid effect, nudge satellites slightly off course over time, requiring small but constant adjustments to keep them in place. Then there's the Moon. Its gravity tugs on satellites, creating oscillations, slowly altering orbital paths over weeks and months. The Sun, far more massive, adds its influence too, its pull affecting trajectories in predictable but powerful ways. Even distant planets have a measurable effect, adding tiny perturbations to orbital paths. In geosynchronous orbit, these forces interact constantly, a complicated ballet of invisible pushes and pulls. Engineers account for them when placing satellites, predicting their orbits years into the future, and programming automatic thruster burns to maintain stability. Without these calculations, a satellite could drift out of position, lose communication with Earth, or collide with another object. Gravity isn't the only invisible force at work. Out here, the Sun dominates the environment. Its light isn't just illumination, it exerts pressure, a gentle push from billions of photons striking a satellite's surface. Over years, this pressure can subtly shift orbits, particularly for small, lightweight satellites. Space agencies call this effect solar radiation pressure, and it must be considered in planning long-term missions. In addition to physical movement, the Sun's energy produces heat, which can expand or warp materials, affecting sensitive instruments and satellite performance. But the Sun brings more than just photons. Streams of charged particles, known as solar wind, blow continuously through the solar system. This wind is invisible, but its effects are profound. It can strip electrons from satellite surfaces, interfere with electronics, and even create currents in circuits that damage systems over time. Sudden bursts, called solar flares or coronal mass ejections, can produce intense radiation storms that disrupt satellite operations or endanger astronauts. Monitoring the Sun isn't optional. It is critical for life and technology in orbit. Space weather forecasts are constantly updated, predicting periods of intense activity and helping engineers adjust satellite operations to minimize damage. These forces, gravity, photon pressure, and solar wind, interact in surprising ways. A satellite drifting slightly off course due to the Moon's pull might be nudged further by radiation pressure, creating a complex path that must be corrected with precise maneuvers. Even tiny adjustments in thruster firings are calculated down to millimeters per second, balancing multiple forces simultaneously. Orbital stability in geosynchronous orbit is not guaranteed. It is achieved and maintained through careful science, planning, and observation. Gravitational dynamics also influence long-term planning for satellite constellations. Mega-constellations like Starlink must consider how satellites interact not only with Earth, but with each other. The combined effects of solar radiation and gravity from Earth, Moon, and Sun can slowly alter orbits, potentially creating collisions if ignored. Sophisticated software tracks every satellite, predicting orbital drift decades in advance. The larger the constellation, the more precise this planning must be, because a single miscalculation can cascade through the network. Solar radiation affects spacecraft beyond orbit positioning. Solar panels, essential for power, are vulnerable to radiation. Prolonged exposure can degrade efficiency, damage circuits, and create charge imbalances. Satellites carry shielding, and engineers design components to resist this constant battering. Instruments measuring weather, GPS, or communications signals must operate despite radiation interference, and every mission must plan for these invisible hazards. The Sun's influence doesn't stop at technology. For spacecraft venturing beyond geosynchronous orbit toward the near-solar neighborhood, solar gravity becomes the dominant force. Trajectories are planned using gravity assists and careful calculations, exploiting the Sun's pull to accelerate spacecraft or redirect them toward targets like Proxima Centauri or TRAPPIST-1. The radiation environment intensifies as the Earth's protective magnetic field fades, exposing instruments and crew to increased risk from cosmic rays and solar particles. Every kilometer farther from Earth increases exposure, requiring careful shielding, monitoring, and timing of maneuvers. Gravitational dynamics also shape the appearance of the orbiting Earth. Tidal forces from the Moon create subtle bulges in Earth's oceans, slightly affecting satellite altitudes. Even in geosynchronous orbit, satellites experience minute variations in distance due to these tidal effects. Engineers factor these into long-term positioning, ensuring that communication signals remain uninterrupted. Every system, from GPS to weather satellites, relies on this invisible balance of forces, maintained continuously. The combination of solar radiation and gravitational forces also shapes debris trajectories. Tiny fragments of satellites, remnants of old missions, or meteoroids can be nudged over years into paths that intersect active satellites. Predicting these collisions is a constant challenge, requiring models that account for every force acting on each object. Even the smallest particles can be dangerous at orbital speeds, and understanding how gravity and radiation interact with debris is critical for maintaining the safety of satellites in geosynchronous orbit. Observing these forces in action gives perspective on scale. The Sun's rays push on lightweight satellites. The Moon's gravity tugs subtly. Earth's gravity anchors everything, and distant planets exert their influence across millions of kilometers. These effects are slow, sometimes imperceptible day to day, but over months or years, they define the orbital environment. Engineers and scientists must think not in hours or days, but in decades, ensuring that satellites continue functioning and avoiding dangerous drift. Even as the Sun shrinks behind Earth on the journey outward, its influence dominates. The gravitational pull from the Sun guides spacecraft paths. Its radiation shapes trajectories and affects instruments, and solar wind continues to batter every exposed surface. Deep space navigation depends on understanding these forces precisely. Without accounting for them, even the most sophisticated spacecraft could drift off target, miss distant stars, or fail to reach planets or exoplanets within the solar neighborhood. In the near solar neighborhood, gravity and solar radiation continue to interact in complex ways. A spacecraft leaving geosynchronous orbit must calculate escape velocity, countering Earth's pull while simultaneously using the Sun's gravity to slingshot toward its next destination. Radiation pressure becomes more pronounced as distance from Earth increases, and solar storms pose risks that can alter trajectories or disable critical instruments. Predicting these combined effects requires detailed modeling, advanced sensors, and continuous observation of both Earth and the Sun. Understanding gravitational dynamics and solar radiation is not optional. It is essential for life and technology in orbit. Every orbit, every maneuver, every satellite's operation depends on predicting how these forces interact. Even the most advanced spacecraft would fail without accounting for the invisible forces shaping their path. As humans expand deeper into the solar system, the lessons learned in geosynchronous orbit, balancing gravity, anticipating solar radiation, and responding to dynamic environmental conditions, become the foundation for every mission beyond Earth. Level 4. Gas giants and their moons. Jupiter, Saturn, and beyond. The moment you move past the inner solar system, everything changes fast. The Sun still burns in the distance, but its warmth thins out, and suddenly the scale explodes. The gas giants are not just bigger planets. They are entire systems of their own. Each one carries moons, radiation, storms, gravity, and magnetic forces so strong they reshape space around them. This is where space stops feeling empty and starts feeling dangerous. Jupiter comes first, and it dominates immediately. It is so massive that it could have become a star if it had gathered just a bit more material when the solar system formed. Its gravity controls the paths of asteroids, bends comets, and protects the inner planets more than once by pulling incoming objects into itself. From a distance, Jupiter looks calm, striped with soft bands of color. But that calm is fake. Those bands are made of clouds moving at hundreds of kilometers per hour, stacked in layers thousands of kilometers deep. As you approach Jupiter, the radiation hits before anything else. The planet's magnetic field is the strongest of any planet in the solar system, so strong that it traps charged particles and accelerates them to extreme energies. This radiation would kill an unprotected human quickly and can damage spacecraft electronics in days. The Juno mission was built like a vault, with thick shielding around its instruments, because Jupiter does not forgive mistakes. Every orbit Juno makes is a calculated risk, flying through radiation zones that no spacecraft had ever dared to pass through before. Then there are the storms. Jupiter's most famous feature, the Great Red Spot, is not a cloud or a mark on the surface. It is a storm larger than Earth that has been raging for centuries. Winds inside it exceed anything measured on our planet, and lightning flashes deep within the clouds. Juno revealed that these storms do not stop at the visible cloud tops. They plunge deep into the planet, driven by heat rising from Jupiter's interior, creating weather systems that extend far beyond anything Earth experiences. Orbiting Jupiter are moons that change everything we thought we knew about where life could exist. Europa looks like a cracked ball of ice, its surface covered in long fractures and ridges. Beneath that ice, scientists are confident there is a global ocean, kept liquid by tidal heating. Jupiter's gravity squeezes Europa as it orbits, generating heat inside the moon the way bending a metal wire warms it up. That heat prevents the ocean from freezing solid, even this far from the Sun. What makes Europa different is not just water. Evidence suggests that this ocean may be in contact with a rocky seafloor, allowing chemical reactions similar to those that support life near Earth's deep-sea vents. The Europa Kuiper mission is designed to fly past this moon repeatedly, scanning the ice, measuring the thickness, and searching for signs that material from the ocean is reaching the surface. If life exists anywhere beyond Earth in our solar system, Europa is one of the strongest candidates. Io, another of Jupiter's moons, is the opposite of Europa. It is the most volcanically active world known. Its surface is constantly reshaped by eruptions driven by the same tidal forces that heat Europa's ocean. Jupiter's gravity stretches Io causing intense friction inside the Moon, melting rock and fueling volcanoes that blast material hundreds of kilometers into space. These eruptions feed Jupiter's magnetosphere, creating glowing auroras around the planet's poles that dwarf anything seen on Earth. As Jupiter falls behind, Saturn takes over the view, and it is impossible to ignore the rings. Flying through them is not a smooth glide through dust. The rings are made of ice chunks ranging from tiny grains to mountain-sized blocks, all orbiting at different speeds. Collisions happen constantly, gentle but relentless, grinding material down over time. Cassini showed that the rings are dynamic, shaped by gravity from Saturn's moons, forming waves, gaps, and sharp edges that change over time. Saturn itself is a world of motion. Winds whip around the planet at incredible speeds, and at its north pole sits a hexagonal storm larger than Earth, locked in place by complex atmospheric dynamics. Cassini watched lightning flash through Saturn's clouds and measured storms that wrap around the entire planet. Beneath the clouds, Saturn generates heat from its own slow contraction, releasing energy that fuels its weather systems. Then there is Titan. At first glance, it looks dull, wrapped in a thick orange haze. But Titan is one of the most Earth-like worlds in the solar system, just with different chemistry. It has rivers, lakes, and seas, not made of water, but of liquid methane and ethane. Rain falls from the sky, carving channels into the surface. Cassini and the Huygens probe revealed shorelines, dunes, and seasonal weather patterns, all driven by hydrocarbons instead of water. Titan's importance goes deeper. Beneath its icy crust, there may be a subsurface ocean of water mixed with ammonia. On the surface, complex organic molecules form in the atmosphere and settle onto the ground. These chemicals are similar to those thought to have existed on early Earth before life began. Studying Titan is like looking back in time, seeing a version of planetary chemistry that may explain how life started here. Enceladus, a smaller moon of Saturn, shocked scientists even more. Cassini detected geysers blasting water vapor and ice particles from cracks near the moon's south pole. These plumes come directly from a subsurface ocean, spraying material into space. By flying through the plumes, Cassini analyzed their composition and found water, organic compounds, and chemical energy sources. This was not indirect evidence. It was material from an ocean sampled without drilling or landing. The implications were immediate. Enceladus has liquid water, energy, and organic molecules, the core ingredients associated with life. And unlike Europa, Enceladus makes its ocean accessible. Future missions could fly through those plumes again, with better instruments, searching directly for signs of biological activity. Beyond Saturn, the solar system grows colder and stranger. Uranus rotates on its side, likely knocked over by a massive collision early in its history. This tilt creates extreme seasons, with poles that face the sun for decades, then plunge into darkness. Uranus's magnetic field is tilted and offset from the planet's center, creating chaotic interactions with the solar wind. Its moons orbit through constantly shifting radiation environments, shaped by a magnetic field that behaves nothing like Earth's. Neptune, farther still, holds the record for the fastest winds in the solar system. Despite receiving little heat from the sun, Neptune's atmosphere is violently active. Storms rise and vanish, dark spots appear and fade, and winds scream through the upper atmosphere at speeds that defy expectations. The planet radiates more energy than it receives, suggesting heat left over from its formation still drives its weather. Neptune's moon. Triton adds another layer of mystery. It orbits backward, unlike most large moons, suggesting it was captured rather than formed in place. Triton has geysers of nitrogen erupting from its surface, driven by seasonal heating. Beneath its frozen crust, there may also be a subsurface ocean, kept warm by tidal forces and internal heat. All of these worlds exist inside powerful magnetic environments. Jupiter and Saturn generate massive magnetospheres that trap radiation and interact with the solar wind, creating vast regions of charged particles. These fields influence everything nearby, from moon surfaces to dust particles. Spacecraft entering these zones must be hardened, shielded, and carefully guided. A wrong trajectory can expose instruments to radiation levels that end missions early. This region of the solar system reshaped how scientists think about habitability. Life is no longer limited to planets close to stars. Moons heated by gravity, hidden oceans sealed beneath ice, and chemical energy independent of sunlight have become central to the search for life beyond Earth. Missions now prioritize ocean worlds, and future spacecraft are being designed to probe beneath ice, sample plumes, and analyze chemistry in detail. Flying through this part of space means moving through systems that behave more like miniature solar systems than planets. Gravity pulls in multiple directions at once. Radiation rises and falls with every orbit. Moons interact, exchange material, and reshape each other over time. The gas giants are not just destinations, they are engines, shaping the architecture of the solar system and rewriting the rules of where life might exist. And beyond them, the darkness deepens, the sun shrinks further, and the next level waits. Level 5. The Kuiper Belt and the edge of the solar system. By the time the Kuiper Belt comes into view, the sun no longer feels like the center of everything. It is still there, still powerful, but it has shrunk into a bright point that no longer dominates the sky. Light weakens, heat fades. Space stretches wider than before. This is where the solar system stops behaving like a tidy family of planets and starts revealing the debris field left behind from its violent birth. The Kuiper Belt is not a thin ring or a neat boundary. It is a vast, uneven region filled with frozen remnants that never became planets. These objects are leftovers from the early solar system, preserved in deep cold, largely unchanged for billions of years. While the inner planets were shaped by collisions, melting, and resurfacing, the Kuiper Belt objects stayed frozen, acting like time capsules from the era when the sun was still forming. Pluto is the most famous of them, but it is not alone. It is one of thousands, possibly millions of icy bodies orbiting far beyond Neptune. For decades, Pluto was nothing more than a blurry dot, its size uncertain, its surface unknown. That changed in 2015, when New Horizons arrived after a journey of nearly 10 years. What it revealed was not a dead frozen rock, but a complex world with mountains, plains, glaciers, and atmosphere. Pluto's surface shocked scientists immediately. Vast plains of nitrogen ice stretch across regions like Sputnik Planitia, flowing slowly like glaciers. Mountains made of water ice rise several kilometers high, meaning they are not fragile frost, but solid structures strong enough to stand against gravity. The surface shows almost no impact craters in some areas, a sign that Pluto is still active, reshaping itself even at this extreme distance from the Sun. Its atmosphere, thin but real, expands and contracts as Pluto moves along its stretched orbit. When it is closer to the Sun, gases freeze less and the atmosphere thickens. When it moves farther away, much of it collapses back onto the surface as ice. This cycle happens over centuries, showing that even here, far beyond planetary warmth, worlds are still dynamic. Pluto's moon system adds another layer. Charon, nearly half Pluto's size, orbits so closely that the two bodies are tidally locked, always facing each other. Smaller moons spin chaotically, tumbling rather than rotating smoothly. Their behavior reveals how fragile and strange gravity becomes in low-energy environments like the Kuiper Belt. Makemake and Haumea tell different stories. Makemake reflects an extraordinary amount of sunlight, meaning its surface is coated in fresh ice, likely methane. It has little to no atmosphere, suggesting volatile gases escape more easily here or freeze permanently. Haumea is even stranger. It spins so fast that it is stretched into an elongated shape, more like a spinning football than a sphere. This rapid rotation likely came from a massive collision early in its history, an impact violent enough to strip material away and form its moons. These objects are not random debris, their orbits reveal patterns. Many are locked in gravitational resonance with Neptune, meaning they complete their orbits in exact ratios, shaped by Neptune's migration outward early in solar system history. This tells scientists that the giant planets did not form where they are now. They moved, scattered material, captured objects, and reshaped the outer solar system as they went. The Kuiper belt matters because it preserves this history. Every object out here carries chemical and structural clues about the original disk of material that surrounded the young sun. Their compositions show what elements were available, how ice is formed, and how early planetary building blocks behaved in deep cold. Studying them is like reading pages torn from the solar system's formation manual. New Horizons did not stop at Pluto. After its historic flyby, it continued deeper into the Kuiper belt, targeting a smaller object once nicknamed Ultima Thule, now known as Arrokoth. This object turned out to be a contact binary, two lobes gently fused together, showing that some Kuiper belt objects formed through slow, soft collisions rather than violent impacts. This confirmed long-standing theories that the outer solar system grew quietly, unlike the chaotic inner regions. Arrokoth's surface showed almost no signs of change since its formation. No melting, no tectonics, no resurfacing. Just preserved structure, frozen chemistry, and a shape that should not exist if collisions were energetic. This single object reshaped models of planet formation, proving that at least part of the solar system formed through gentle accumulation rather than constant destruction. Beyond the main Kuiper belt lies the scattered disk. Objects here have highly stretched orbits, flung outward by gravitational interactions with Neptune. These bodies travel far from the Sun before swinging back in, bridging the region between the Kuiper belt and the more distant Oort cloud. Some of them may become long-period comets, sent inward after subtle gravitational nudges from passing stars or galactic tides. This is where the edge of the solar system begins to blur. There is no sharp border. Instead, there is thinning material, longer orbits, and increasing isolation. The Sun's gravitational grip weakens, and objects move more slowly, taking centuries or even millennia to complete a single orbit. Light becomes scarce. Temperatures drop to levels where most gases are permanently frozen. The beginnings of the Oort cloud are hinted at here. While the Oort cloud itself lies far beyond direct observation, its influence is felt. Some Kuiper belt objects appear to be transitioning outward, nudged by planetary gravity and stellar encounters. These bodies represent the early stages of the cloud that surrounds the solar system, like a distant halo, a reservoir of comets extending nearly halfway to the nearest stars. Approaching these icy worlds feels different from approaching planets. There are no thick atmospheres to glow, no strong sunlight to reflect. Surfaces appear muted, textured, ancient. The silence feels heavier, not because sound is absent, but because motion slows. Orbits stretch. Everything takes longer. A spacecraft drifting here moves through an environment where change happens on geological timescales that make human history irrelevant. Yet this region is not dead. Chemical processes continue at low energy. Radiation from cosmic rays alters surface chemistry over millions of years, slowly darkening ice, creating complex organic compounds. These changes happen molecule by molecule, shaping surfaces without heat or pressure. Even in deep cold, chemistry never fully stops. The Kuiper belt also defines what the solar system is not. Beyond it, the Sun no longer dominates. Gravity begins to compete with the pull of nearby stars and the tidal influence of the Milky Way itself. Objects here are the last ones still clearly bound to the Sun, still part of its family, before interstellar space begins to assert itself. Understanding this region reshapes how planetary systems are viewed everywhere else in the galaxy. Observations of debris disks around other stars suddenly make sense when compared to the Kuiper belt. What looks like distant dust clouds are likely similar belts of frozen remnants shaped by unseen planets carrying the same signatures of migration, collision, and preservation. As spacecraft push farther outward, signals weaken, commands take longer, and navigation becomes an exercise in patience and precision. New Horizons now operates in a realm where sunlight is barely strong enough to power its instruments. Yet it continues sending data across billions of kilometers. Its journey is not just exploration. It is proof that the solar system does not end where planets stop. The Kuiper belt is not a boundary. It is a transition, a place where the familiar rules begin to loosen, where the sun's influence fades gradually instead of snapping off, and where the material that built worlds still drifts, frozen and untouched, waiting to be read. Beyond this, space becomes something else entirely. Level 6. The Oort cloud, the solar system's outer edge. By the time the Oort cloud becomes relevant, the solar system has already stopped looking familiar. Planets are long gone. The Kuiper belt is far behind. Even Pluto feels close compared to what comes next. Distance here is no longer measured in millions or billions of kilometers. It is measured in astronomical units stacked by the thousands. At this scale, the sun's pull weakens enough that the solar system starts to blur into interstellar space. The Oort cloud is not a solid shell or a visible structure. It is a vast spherical region surrounding the solar system, stretching from about 1,000 astronomical units to possibly 100,000 astronomical units from the sun. That outer edge could be nearly halfway to the nearest star. Light from the sun takes weeks to reach the inner edge and over a year to reach the outermost regions. From here, the sun is no longer a blazing disk. It is a bright star among many, barely larger than the others. This region is made of ice, rock, and frozen gases left over from the early solar system. These objects never formed into planets. Instead, they were thrown outward during the chaotic early movement of the giant planets. Jupiter, Saturn, Uranus, and Neptune scattered material outward with their gravity, flinging billions of icy bodies into distant orbits. Some were ejected completely into interstellar space. Others slowed just enough to remain weakly bound to the sun. Over time, these scattered objects formed a loose, distant cloud. Not flat like the Kuiper belt, but spherical, extending above and below the plane of the planets. This shape matters. It shows that the Oort cloud was shaped not just by the planets, but by outside forces. Passing stars' molecular clouds and the gravitational tide of the Milky Way itself slowly reshaped these orbits over billions of years. The Oort cloud explains something that once made no sense: long-period comets. These comets appear suddenly, approach the sun from random directions, and then disappear for tens of thousands or even millions of years. Their orbits are stretched into extreme ellipses, far too long and tilted to come from the Kuiper belt alone. The only place they can come from is a distant spherical reservoir. When one of these icy bodies is disturbed, its long sleep ends. A passing star drifting near the solar system can shift its orbit slightly. The gravitational pull of the Milky Way can do the same over time. Even small changes are enough. At these distances, gravity is weak. A gentle nudge can send an object falling inward toward the sun. As it approaches, the comet begins to change. Ice that has been frozen solid for billions of years starts to heat up. Gases trapped inside expand and burst outward, forming a glowing coma and a tail that stretches millions of kilometers. These comets are not just visual spectacles. They are ancient material, older than Earth itself, delivering samples of the early solar system straight into the inner regions. Every long-period comet observed strengthens the case for the Oort cloud. No telescope has ever directly imaged it. It is too distant, too diffuse, too dark. Its existence is built from motion, mathematics, and repeated observation. Orbits traced backward always point to the same distant source. Models that include the Oort cloud explain what we see. Models without it fail. Recent surveys have added weight to this idea. Modern sky scanning projects detect comets earlier than ever before, tracking their paths with extreme precision. These data show orbital patterns that match predictions made decades ago. Some comets arrive with trajectories altered before they even reach the planets, showing signs of interaction with galactic forces rather than planetary ones. The Oort cloud also changes how we think about the solar system's boundaries. This is not just a leftover junk zone. It is the outer structure that defines the Sun's gravitational reach. Beyond it, objects are no longer meaningfully bound. They drift freely among the stars. The solar system does not end at Neptune or Pluto. It fades gradually through this frozen halo. This region may also hide something larger. The idea of Planet 9 comes from strange clustering in the orbits of distant objects. Several bodies in the outer solar system share similar orbital orientations that are difficult to explain by chance. One explanation is a large, unseen planet, several times the mass of Earth, orbiting far beyond Neptune. If Planet 9 exists, it would likely move through the inner regions of the Oort cloud or the scattered disk. Its gravity could explain why some objects are pulled into unusual orbits. It could also shape the distribution of comets, subtly influencing which ones get sent inward. Searchers continue using infrared surveys and deep sky scans, but at these distances, even a large planet reflects little light. The possibility of Planet 9 matters because it would change how we understand the solar system's formation. A planet that far out could have been captured from another star or thrown outward during early planetary migration and somehow stabilized. Either scenario points to a solar system that was once far more chaotic than it appears today. The Oort cloud is also shaped by the galaxy itself. The Milky Way's gravitational field stretches and pulls on distant objects, especially those at the outer edge of the cloud. As the Sun orbits the center of the galaxy, it passes through regions with slightly different gravitational environments. Over hundreds of millions of years, this galactic tide gently stirs the cloud, sending waves of comets inward. Passing stars matter too. The Sun does not move through empty space. It drifts among other stars, sometimes coming relatively close. Even a star passing a few light years away can disturb the outer Oort cloud. These encounters are rare on human timescales, but common over billions of years. Each one reshapes orbits slightly, keeping the cloud active. Approaching this region in imagination means leaving behind almost everything familiar. The sky darkens, the sun dims until it no longer lights surfaces, but merely marks direction. Objects drift silently, separated by enormous distances. There is no sense of orbit the way planets have. Motion is slow, almost suspended. A single object may take millions of years to complete one path around the Sun. Temperatures here are only a few degrees above absolute zero. Most substances are frozen harder than rock. Volatile gases like hydrogen, methane, and nitrogen are locked solid. Radiation from distant stars and cosmic rays becomes more important than sunlight. Over vast timescales, this radiation alters surface chemistry, slowly building complex organic compounds on icy surfaces. This is why the Oort cloud matters for more than comet paths. It is a storage zone for primitive chemistry. If comets from this region delivered water and organic molecules to Earth early in its history, then the Oort cloud indirectly shaped life itself. Every long-period comet carries the same potential cargo, frozen chemistry preserved from before planets existed. The cloud also connects the solar system to interstellar space. Objects at its outer edge are barely bound. A strong enough disturbance can remove them completely, sending them drifting between stars. Likewise, the Sun may capture objects from other systems as it moves through the galaxy. Some of the Oort cloud's contents may not even be native to our solar system. This means the Oort cloud is not just ours. It is part of a larger exchange. Stars trade material over time, seeding each other's outskirts with debris. What we call the solar system is not sealed. It leaks, absorbs, and interacts with the galaxy in slow, subtle ways. Spacecraft have never reached the Oort cloud. Voyager 1 and 2, even after decades of travel, are only entering the heliopause, where the solar wind gives way to interstellar space. Reaching the inner edge of the Oort cloud would take thousands of years with current technology. Everything we know comes from indirect evidence, careful observation, and physics tested closer to home. Yet despite its distance, the Oort cloud is active. It sends visitors inward. It responds to forces beyond the sun. It preserves ancient material. It defines the outer edge of what it means to belong to this star. Beyond it, the solar system no longer holds together the way it once did. Gravity loosens, the sun's authority fades, and space stops being organized around a single center. Level 7. Interstellar space, between the stars. Interstellar space begins the instant the sun loses control, not metaphorically, not emotionally, physically. There is a real boundary where the solar wind, the constant stream of charged particles blown outward by the sun, finally weakens enough that it can no longer push back against the pressure of the galaxy itself. That boundary is called the heliopause, and it sits roughly 120 astronomical units from the sun. Past this point, the space around you is no longer shaped mainly by our star. It belongs to the Milky Way. Nothing dramatic marks the crossing. No wall, no flash, no sudden darkness. Instruments detect it before eyes ever could. Particle densities change, magnetic fields shift direction, the pressure balance flips. This is how scientists knew Voyager 1 had crossed the line in 2012, not by seeing something new, but by measuring what was no longer there. The solar wind dropped, galactic particles surged, the sun's influence faded into background noise. Voyager 1 did not slow down or change course. It simply kept going, carrying humanity's first physical presence into true interstellar space. Voyager 2 followed years later, confirming the crossing with different instruments and a slightly different trajectory. Together, they turned interstellar space from theory into measured reality. Out here, space is not empty. It only looks that way because our instincts are shaped by planets and stars. Interstellar space is filled with the interstellar medium, a thin mixture of gas, dust, radiation, and magnetic fields spread across vast distances. The density is low by Earth standards, but across light years, it adds up to enormous mass. This material is the raw substance from which stars and planets form, recycled again and again across cosmic time. Most of this medium is hydrogen, drifting as individual atoms or weakly bound molecules. Helium follows, along with trace elements forged inside stars that exploded long before the sun existed. Oxygen, carbon, nitrogen, iron, all of them float here in microscopic amounts, waiting. Dust grains made of carbon compounds or silicates drift between stars, absorbing light, scattering radiation, and seeding future systems. Cosmic rays move through this region constantly. These are not rays in the usual sense, but high-energy particles accelerated by supernova explosions, black hole jets, and violent stellar events across the galaxy. They travel at near-light speed and pass straight through planets, spacecraft, and human bodies. Earth is shielded by its atmosphere and magnetic field. Interstellar space offers no such protection. This radiation environment is one of the defining features of space between the stars. It shapes chemistry, alters materials, and poses a major challenge for any future attempt at human or robotic travel beyond the sun's influence. Electronics degrade faster, materials become brittle. Living tissue would be damaged without heavy shielding. Magnetic fields thread through interstellar space like invisible highways. They are weak compared to those near planets, but they extend across enormous regions. These fields guide charged particles, influence star formation, and interact with stellar winds when stars move through them. The heliosphere itself, the bubble created by the sun's wind, is shaped and compressed by these galactic fields as the solar system moves through the Milky Way. The sun is not stationary. It orbits the center of the galaxy once every 200 million years, drifting through different interstellar environments along the way. Dense clouds, thin voids, regions rich in dust, all of these have influenced the solar system's past and will shape its future. The heliosphere expands and contracts depending on what the sun is moving through. Interstellar space pushes back. Voyager's instruments detected this interaction directly. Beyond the heliopause, the density of galactic cosmic rays increased sharply. The orientation of the magnetic field changed, aligning more closely with the galaxy's field, rather than the sun's. These measurements confirmed that the spacecraft had entered a region governed by forces far larger than any single star. Sound does not exist here. Light does, but it is faint and scattered. The nearest stars appear brighter than they did from within the heliosphere, no longer filtered by the sun's bubble. The background glow of the galaxy becomes more noticeable. Radiation hums through space, invisible but relentless. The interstellar medium is not uniform. It has structure. Filaments, clouds, and cavities stretch across light years. Some regions are warmer and ionized, glowing faintly. Others are cold and dense, collapsing slowly under gravity, beginning the long process of star formation. The solar system is currently passing through a relatively sparse region known as the local interstellar cloud, a pocket of thin gas surrounded by more turbulent areas. Every star system lives inside this medium. The Sun is not special in that sense. What makes interstellar space important is that it connects all stars together. Material ejected from dying stars becomes part of the medium. That material later collapses to form new stars and planets. The atoms in your body once drifted through interstellar space, long before Earth existed. From here, the solar system looks small. The Sun is just another star, trailing a faint bubble of particles behind it as it moves through the galaxy. The planets are invisible. Even the Kuiper belt and Oort cloud blur into insignificance against the scale of interstellar distances. Voyager's signals take more than 20 hours to reach Earth now, traveling at the speed of light across billions of kilometers. Even that is nothing compared to the distances ahead. At its current speed, Voyager will take tens of thousands of years to approach another star closely, and even then, it will not stop. Interstellar space does not have destinations the way planetary systems do. It is a passage, not a place. Dust grains occasionally collide with spacecraft here at extreme relative speeds. Even a grain smaller than a grain of sand can cause damage when moving fast enough. These collisions are rare but real, another reminder that interstellar space is active, not empty. The interstellar medium also carries faint radio signals, background radiation left over from the early universe, and emissions from distant sources. This noise becomes clearer beyond the heliosphere, no longer drowned out by solar interference. Instruments listening from here hear the galaxy more cleanly than ever before. This region marks a psychological shift as much as a physical one. Everything familiar is behind you. Gravity no longer curves paths around planets. Orbits stretch into near straight lines. Motion becomes inertia. Once something is moving, it keeps moving, largely undisturbed, sometimes for millions of years. Interstellar space is where the solar system dissolves into the galaxy, not abruptly, gradually. Influence fades, identity blurs, the Sun's authority weakens until it becomes just one gravitational source among many. And beyond this, the distances grow so large that even stars stop feeling close. The discovery of rogue planets and free-floating objects. Interstellar space is crowded in ways most people never imagine. Between stars, far from any sun, entire worlds are moving through darkness without belonging to anything. These are rogue planets, also called free-floating planets, objects with the mass of planets that do not orbit a star at all. They drift alone through interstellar space, following paths shaped only by gravity from distant stars and the slow pull of the galaxy itself. For decades, these objects were only theoretical. Astronomers assumed they must exist because planetary systems are violent places. Young stars form surrounded by disks of gas and dust, and as planets grow, they interact. Large planets move inward and outward. Orbits cross. Gravity slingshots smaller worlds away. Some planets collide. Others are thrown completely out of their systems, launched into interstellar space with no star to return to. The first solid evidence came quietly. Astronomers noticed brief, unexplained flashes of light from distant stars. These flashes were not explosions or flares. They were gravitational lensing events. Something massive passed in front of a background star, bending its light for a short time before moving on. The object doing the bending was invisible, producing no light of its own. When these events were analyzed, the masses matched planets. Not stars, not brown dwarfs, planets. Surveys began to find more of them, then many more. Some estimates now suggest there may be as many rogue planets in the Milky Way as there are stars, possibly more. Billions of worlds, untethered, moving freely through interstellar space. Some are likely gas giants, massive and cold. Others appear to be Earth-sized. A few may even be larger than Jupiter. These objects are not rare accidents. They are a natural outcome of planet formation. Star systems do not keep everything they create. Drifting through interstellar space, these planets move past stars at distances measured in light years. A rogue planet can pass through a stellar neighborhood, briefly catching faint warmth from a nearby sun, then disappear back into darkness for millions of years. There is no sunrise or sunset, no orbit, just motion. Despite the cold, some of these planets may not be completely frozen. Heat left over from their formation can remain trapped inside for billions of years. Thick atmospheres, if present, can slow the loss of that heat. Radioactive elements in their cores can add more energy. In theory, subsurface oceans could exist beneath ice layers, completely isolated from starlight. These worlds are invisible unless they cross the line of sight to a star or glow faintly in infrared surveys. Most of them will never be seen directly. They move silently through clouds of hydrogen and helium, the most common elements in the galaxy. These clouds dominate interstellar space. Hydrogen fills enormous regions between stars, sometimes as thin individual atoms, sometimes grouped into molecules. Helium floats alongside it, chemically quiet but abundant. Together, they form massive clouds that stretch across dozens or hundreds of light years. From inside these clouds, stars appear dimmer and redder, their light scattered and absorbed. Traveling through one of these clouds means moving through a medium that is thin by Earth standards, but immense by volume. A spacecraft would pass through regions where hydrogen atoms collide with its surface at high speed, slowly eroding materials over extreme timescales. Dust grains drift through these clouds as well, microscopic but fast enough to matter over long distances. Stars appear widely spaced here. Even the closest ones are years away at light speed. Moving through this environment feels like drifting through a vast ocean where islands are impossibly far apart. The galaxy does not feel packed. It feels stretched. Within this space, free-floating objects are not alone. They share the medium with debris, dust, and occasional visitors from other star systems. That reality became undeniable in 2017. Astronomers detected an object entering the solar system on a trajectory that made no sense. It was moving too fast. Its path was not bound to the sun. It came from outside and would leave again. This was not a comet from the outer solar system. This was something else. It was named Oumuamua. Oumuamua did not behave like any asteroid ever seen. It showed no clear tail, yet it accelerated slightly as it moved away from the sun. That acceleration suggested outgassing, but not the kind seen in normal comets. No dust plume followed it. No familiar signature appeared. Its shape was inferred from how its brightness changed as it rotated. The variation was extreme. It appeared to be far longer than it was wide, unlike typical solar system objects. Its surface reflected light in a way that suggested it had been exposed to cosmic radiation for an incredibly long time, altering its outer layers. Everything about Oumuamua pointed outward. Its speed matched what would be expected for an object drifting through interstellar space before being briefly captured by the sun's gravity. Its trajectory traced back to the general motion of stars in our galactic neighborhood. It did not originate from any known region of the solar system. This was the first confirmed interstellar object ever observed passing through. It arrived silently. It left just as quietly, and it was gone before humanity truly understood what it was seeing. The implications were immediate. If one interstellar object passed through during the short time humans have been watching carefully, then many more must pass through unnoticed. Interstellar space is not sealed off from star systems. Objects move between them. 2 years later, another visitor arrived. This one behaved differently. Comet Borisov entered the solar system in 2019, and unlike Oumuamua, it looked familiar at first glance. It developed a coma, it grew a tail, it released gas and dust as it approached the Sun. But its orbit told the same story. It was not bound, it came from interstellar space. What made Borisov important was time. Astronomers detected it early enough to observe it in detail. Spectroscopy revealed its chemical makeup. The ratios of certain gases differed from comets native to our solar system. It formed somewhere else, around another star, under different conditions. This was not theory anymore, this was sampling. Material formed around another star had entered our solar system, been studied, and left again. Together, Oumuamua and Borisov confirmed something fundamental. Interstellar space is not empty space between isolated systems. It is a shared environment where material moves, mixes, and occasionally intrudes. Rogue planets drifting through hydrogen clouds. Interstellar objects crossing stellar neighborhoods. Comets carrying chemistry from distant systems. This is normal galactic behavior. Stars move. Systems evolve. Gravity rearranges everything over time. Drifting past stars light years away means understanding that distance is not protection. Given enough time, paths cross. Objects wander. What seems impossibly far becomes reachable on cosmic timescales. Hydrogen and helium clouds act as highways and slow zones at once. They do not stop objects, but they shape their environments. They influence temperature, radiation exposure, and chemistry. Free-floating objects passing through them carry those interactions forward. A rogue planet moving through such a cloud might accumulate surface frost or lose atmosphere through long exposure. An interstellar object like Oumuamua may have had its surface altered repeatedly by radiation and particle impacts, long before it ever reached our solar system. Nothing about interstellar space is static. It is motion without ownership. Objects here are not destinations. They are travelers. And now that humanity has seen them, measured them, and tracked them, interstellar space is no longer theoretical distance. It is an active region filled with worlds, debris, and visitors, all moving through the galaxy, whether we are watching or not. Level 8. The local stellar neighborhood nearby star system. Within 20 light-years of Earth, the galaxy stops being abstract and starts becoming mapped territory, not because it suddenly becomes safe or familiar, but because individual stars emerge as distinct systems with measurable planets, gravitational interactions, and histories that can be reconstructed through observation rather than inference. This region is known as the local stellar neighborhood, and it contains dozens of star systems moving together through the Milky Way, each with its own architecture, its own planetary remnants, and in some cases, worlds that orbit close enough to liquid water conditions to make them scientifically unavoidable. Alpha Centauri dominates this neighborhood not because it is unusual, but because it is close enough for its complexity to be studied in detail. It is not a single star, but a gravitationally bound system, consisting of 3 members, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, each following predictable paths around a shared center of mass. Alpha Centauri A and B form a binary pair, orbiting each other at distances comparable to the orbit of Saturn around the Sun, while Proxima Centauri trails further out, weakly bound, but still part of the same stellar family. Alpha Centauri. A closely resembles the Sun in mass, temperature, and luminosity, making it a natural comparison point for understanding how typical or atypical our own star may be. Alpha Centauri B is slightly smaller and cooler, but still stable, still long-lived, and still capable of supporting planetary systems with long orbital lifetimes. The fact that these 2 stars orbit each other does not prevent planet formation, but it does complicate it, forcing planets into tighter orbits or more carefully balanced configurations to remain stable over billions of years. Proxima Centauri, however, changes the entire conversation because unlike its larger companions, it is a red dwarf, small, faint, and highly active, producing frequent stellar flares that bathe nearby space in bursts of radiation. Red dwarfs are the most common type of star in the galaxy, which means that what happens around Proxima Centauri is not an edge case, but a preview of conditions around countless other stars scattered throughout the Milky Way. The discovery of Proxima Centauri b transformed this system from a point of curiosity into a focal point of modern astronomy, because the planet orbits squarely within what is known as the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planetary surface under the right conditions. Proxima b completes an orbit in just over 11 days, which places it extremely close to its star. But proximity does not automatically mean uninhabitable when the star itself emits far less energy than the Sun. The challenge lies in the environment rather than the distance. Proxima Centauri's flares raise questions about atmospheric erosion, radiation exposure, and long-term stability, but none of these factors automatically disqualify the planet. Instead, they define the conditions that any potential atmosphere would need to survive, forcing scientists to rethink habitability not as a narrow Earth clone scenario, but as a spectrum of possible stable states shaped by stellar behavior. Barnard's star sits just 6 light-years away and moves through space faster than almost any other star in the sky, its rapid motion revealing its proximity long before modern instruments could measure its distance accurately. Like Proxima Centauri, Barnard's star is a red dwarf, faint and cool, but exceptionally old, likely formed when the galaxy itself was much younger. Its age makes it valuable, because any planets orbiting it would have experienced extraordinarily long periods of stability, assuming they survived early formation chaos. For decades, Barnard's star was suspected of hosting planets, but early claims collapsed under scrutiny, leaving it as a cautionary tale about over-interpreting limited data. That changed with improved radial velocity measurements, which revealed subtle but consistent gravitational effects, consistent with at least one planetary companion. Barnard's star B, a super-Earth candidate, orbits beyond the traditional habitable zone, making it cold by Earth standards. But its existence confirms that even ancient stars can retain planetary systems over immense spans of time. The importance of Barnard's star does not come from the habitability of its known planet, but from what it demonstrates about planetary survival and system longevity. A planet that has remained bound to such an old star provides constraints on how planetary orbits evolve, how atmospheres are lost or retained, and how stellar activity changes over cosmic time. Wolf 359 lies slightly farther out, but remains within the 20 light-year boundary, and it represents the more extreme end of red dwarf behavior. Smaller, dimmer, and far more active, Wolf 359 produces intense flares that can dramatically alter conditions in surrounding space. Any planets orbiting close enough to receive significant warmth would be subjected to frequent radiation bursts, making atmospheric retention difficult unless protected by strong magnetic fields or dense atmospheres. Despite these challenges, Wolf 359 remains a target of exoplanet searches, because red dwarfs concentrate their habitable zones extremely close to the star, which makes planets easier to detect through both transit and radial velocity methods. The absence of confirmed Earth-like planets around Wolf 359 so far does not rule them out, but it emphasizes the diversity of conditions even among stars of similar size and type. Across the local stellar neighborhood, exoplanet discoveries have reshaped expectations. Planets appear around nearly every type of star observed closely enough, and small rocky planets are not rare. Habitable zones are not fixed rings, but dynamic regions shaped by stellar luminosity, activity, and planetary atmosphere, meaning that habitability cannot be reduced to distance alone. Earth-like candidates within 20 light-years are valuable not because they promise life, but because they allow direct testing of atmospheric composition, climate models, and planetary evolution using future telescopes. The closer the system, the more photons can be collected, the more detailed the spectra, and the greater the chance of distinguishing between barren rock and chemically active worlds. What emerges from this region is not a picture of isolated stars scattered randomly through space, but a structured environment where stellar motion, gravitational interactions, and shared galactic history link systems together. These stars were not born where they are now, and their planets carry chemical fingerprints of the interstellar clouds that formed them. The local stellar neighborhood is therefore not just a list of nearby suns, but a laboratory where theories of planet formation, habitability, and stellar evolution intersect under conditions that can actually be measured. Each system adds constraints, removes assumptions, and replaces speculation with data, slowly transforming the question of whether Earth is unique from a philosophical one into a technical one. And within 20 light-years, that question is no longer distant. It is observational. The interstellar travel concepts. Breakthrough. Interstellar travel stops being theoretical the moment propulsion shifts from fuel to physics. And that shift is exactly where concepts like breakthrough starshot enter the picture, not as distant dreams, but as engineered responses to the limits of chemical rockets. The distances between stars make traditional propulsion useless, because even the fastest spacecraft ever built would take tens of thousands of years to cross a single light year. And that reality forces a different approach, one that treats light itself as the engine. Breakthrough Starshot proposes something radically simple and technically brutal, a spacecraft reduced to its absolute minimum mass, no crew, no fuel tanks, no onboard propulsion, just a light sail thinner than paper attached to a chip-scale probe carrying cameras, sensors, and transmitters. Instead of carrying energy, the craft receives it from Earth, where an array of powerful ground-based lasers would focus their beams onto the sail, accelerating the probe outward until it reaches a significant fraction of the speed of light. At those velocities, interstellar space stops feeling empty, because hydrogen atoms, dust grains, and stray particles become high-energy hazards, turning even microscopic collisions into potential damage. This is why the design emphasizes redundancy through numbers, launching swarms of probes rather than a single flagship, accepting losses as part of the journey rather than failures. Once acceleration ends, the probe coasts, silent and unpowered, crossing the gap between stars in decades rather than millennia. During that time, it passes through regions of space shaped by forces that never touch planetary environments, clouds of hydrogen stretched thin across light years, faint dust lanes illuminated only when starlight scatters through them, and radiation fields that vary depending on proximity to massive stars or remnants of stellar death. Light sails make this possible because photons carry momentum, and when enough photons strike a reflective surface, that momentum adds up. There is no thrust plume, no exhaust, no fuel consumption, just continuous pressure pushing outward, a method that scales not with mass carried on board, but with energy supplied from afar. The physics is already proven, demonstrated by solar sails that use sunlight itself as propulsion. But Breakthrough Starshot pushes the concept to an extreme by replacing the sun with a controlled laser system. As the probe leaves the solar system, familiar stars fade behind it, and ahead the sky reorganizes, not because new stars appear, but because perspective changes. Nearby stars grow brighter long before they grow larger, their light blue shifted by the probe's velocity, while distant stars dim and redden. The craft is not drifting aimlessly. It is slicing through the local stellar environment, where star types vary dramatically in temperature, mass, and lifespan. Red dwarfs dominate this region, small, long-lived stars that burn their fuel slowly and steadily, often hosting compact planetary systems with tightly packed orbits. Passing near one reveals intense magnetic activity, frequent flares, and strong stellar winds that carve cavities in surrounding interstellar gas. Yellow stars like the Sun are rarer, more massive, and shorter-lived. Their planetary systems often more spread out, their habitable zones farther from the star. More massive stars, blue and white, burn fast and die young, and while few exist close to Earth, their influence stretches far, shaping nebulae and ionizing gas clouds long after they form. When such stars explode as supernovae, they leave behind expanding shells of energized gas, supernova remnants that glow across the electromagnetic spectrum, rich with heavy elements forged in the explosion itself. Passing through a supernova remnant is not like crossing debris because space remains mostly empty, but the radiation environment changes sharply, and the density of charged particles increases. These regions are where cosmic rays are accelerated, where shock fronts ripple through gas clouds, compressing material that may one day form new stars and planets. Nebulae mark different stages of this cycle. Some are stellar nurseries, dense clouds of gas and dust collapsing under gravity. Others are the remains of stars that have shed their outer layers, illuminated by hot cores left behind. To an interstellar probe, these structures are not colorful clouds, but gradients of density and radiation, regions where particle counts rise and fall, where magnetic fields twist and reconnect. As the probe approaches another star system, its primary mission begins. At relativistic speeds, it has only hours or days to collect data, imaging planets as they streak past, analyzing atmospheres through brief spectroscopic measurements, and recording magnetic and radiation environments. There is no orbit insertion, no second chance, only a single flyby compressed into a narrow window. This urgency is why target selection matters and why recent exoplanet discoveries drive interstellar mission planning. Candidate planets for future observation are chosen not because they resemble Earth perfectly, but because they offer measurable signals, atmospheres thick enough to analyze, temperatures within detectable ranges, and orbital configurations that allow clear separation from stellar glare. The latest discoveries have expanded this list rapidly. Nearby systems have revealed rocky planets in tight orbits, super-Earths with dense atmospheres, and multi-planet systems where gravitational interactions provide clues about internal structure and composition. Each detection refines models of planet formation and survival, narrowing down which systems justify the risk and cost of interstellar probes. Future observations aim to identify planets with atmospheric signatures that can be distinguished even during high-speed flybys, molecules that absorb or emit light in recognizable patterns. These targets are not promises of life, but they are benchmarks, worlds that can test instruments, validate theories, and turn interstellar travel from a symbolic gesture into a data-driven enterprise. Light sail probes would relay their findings back to Earth using tightly focused laser communication, transmitting across light years with signals that weaken as distance grows, requiring precise aiming and long integration times. The data would arrive years after collection, fragments of information assembled into images, spectra, and particle measurements that represent humanity's first direct samples of another star system. Interstellar travel at this scale does not rely on breakthroughs in materials alone, but on coordination, precision, and patience. The launch infrastructure must deliver enormous energy in short bursts, the sails must survive extreme acceleration, and the probes must remain functional after decades in deep space, exposed to radiation levels far beyond those encountered by planetary missions. As technology advances, candidate planets for observation will shift, updated by each new discovery, each refined measurement. Some systems will be deprioritized as hostile or uninformative, while others will rise to prominence because their planets offer rare combinations of size, temperature, and atmospheric depth. Through this process, interstellar space stops being an abstract gap and becomes a mapped environment, shaped by stars, remnants, and clouds, navigated not by instinct, but by physics. Breakthrough starshot and light sails represent the first credible step into that environment, not as passengers, but as observers moving fast enough to bridge the distance within a human lifetime. And once that boundary is crossed, the idea of future observation changes permanently, because stars are no longer unreachable points of light, but destinations defined by data, motion, and measurable paths through the space between them. Level 9, the Milky Way galactic scale. Flying above the plane of the Milky Way is unlike anything seen from within the solar system. From this vantage, the galaxy is not a blur of stars, but an organized spiraling structure, a vast system stretching over 100,000 light-years, with billions of stars embedded in a dynamic interwoven pattern. Spiral arms curve gracefully outward, dense with stars, gas and dust, forming lanes that are brighter and more active than the spaces in between. Yet even in their brightness, there is subtle variation, with pockets of extreme density where star formation occurs, and calmer regions where older stars drift almost alone. Each arm is not merely a line of stars, but a turbulent zone, a mix of luminous, massive young stars, clusters of protostars still forming from the gas and dust in the surrounding nebulae, and ancient stars that have completed billions of years of life, wandering towards the interarm spaces. The view from above reveals these spirals as a structural blueprint, a map of activity and history, showing both where stars have formed and where they will form next. The galactic center dominates this structure, a region compact yet unimaginably massive, containing a concentration of stars millions of times greater than our local neighborhood, packed tightly and orbiting around a single, supermassive black hole known as Sagittarius, a star. From a distance, this center glows faintly, obscured by thick interstellar dust lanes. But its gravitational pull shapes the orbits of stars throughout the inner galaxy. Stars near the center move at incredible speeds, their paths twisted by the gravitational influence of Sagittarius A star, creating phenomena such as stellar streams, eccentric orbits, and close encounters that can fling stars into wider galactic paths or destabilize orbiting systems entirely. The dynamics here are intense, and yet the black hole itself is calm in terms of observable activity for much of the time, quietly anchoring the surrounding mass. A silent architect controlling the motion of everything within several light-years. Between the spiral arms and the galactic center, star formation is constant. Dense molecular clouds, sometimes spanning dozens of light-years, collapse under gravity to form new stars, regions where heat and radiation push outward against collapsing gas, while nearby stellar winds carve cavities and shock fronts into the surrounding medium. These are the cradles of stellar life, visible across the galaxy as glowing nebulae, shining in the light of newly born stars whose ultraviolet radiation excites surrounding hydrogen gas. Flying above them, the view shows the turbulence and structure within these clouds, filaments of gas, pockets of dust dense enough to obscure light, and nascent stars glowing faintly from the energy of their first nuclear reactions. Star formation here is not uniform. It is influenced by previous generations of stars, by supernova shockwaves, by magnetic fields threading through the gas. The entire galaxy is a web of cause and effect, where one stellar birth can trigger another or leave regions dormant for millions of years. Supernova remnants are scattered throughout the spiral arms, bright in X-ray and radio observations, their material expanding outward and enriching the interstellar medium with heavy elements. These remnants are the aftermath of massive stars that ended their lives explosively, releasing energy sufficient to compress surrounding gas and sometimes trigger new waves of star formation. Flying through the galaxy above these remnants, one can observe the complexity of these structures, expanding shells of hot gas, filaments twisted by magnetic fields, and clumps of material dense enough to collapse again, carrying the legacy of stellar death into the next generation of stars. The presence of these remnants throughout the arms reminds us that the galaxy is not static. It is constantly cycling matter and energy, recycling material into new stars and planets while scattering the remains of the old. Pulsars and neutron stars dot the galactic plane, compact remnants of supernova explosions, spinning rapidly and emitting beams of radiation detectable across great distances. Their presence is subtle visually, invisible to the naked eye, but they are key markers of the life cycle of stars and the high-energy processes that dominate the galactic environment. Some pulsars rotate hundreds of times per second, their rotation rates slowing only over millions of years, their radiation detectable as precise, rhythmic pulses. Neutron stars with stronger magnetic fields, magnetars, exhibit sudden bursts of energy, violent flares that can affect the local interstellar medium, compressing gas and influencing nearby star formation. Observing these objects from above the plane allows a perspective on their distribution and frequency, showing them concentrated in regions with historical star formation, particularly within spiral arms where massive stars were more common. The galactic plane itself is a dynamic, structured environment, not a uniform disk. Flying across it, there is an interplay between bright stellar regions, darker dust lanes, and interspersed nebulae, forming a complex tapestry where distance, density, and stellar age vary dramatically. Gas clouds, both ionized and molecular, shift under gravity, forming arches and filaments that guide the motion of new stars. Dense clusters of stars create local gravitational wells, slightly warping the plane and affecting the orbits of surrounding objects. The motion is continuous, imperceptible on human timescales, but evident in detailed models of galactic kinematics, showing the Milky Way as a living, moving system rather than a static backdrop of stars. Flying above the galaxy reveals billions of stars spread along the plane, some in clusters, some isolated, each with its own system of planets or remnants. Globular clusters, spherical and dense, orbit the galaxy at larger distances, carrying ancient stars that predate the formation of the spiral arms themselves. Observing them in the context of the Milky Way from above emphasizes scale. While the plane is populated with hundreds of billions of stars, the clusters are compact islands of ancient stellar history, each a relic from early galactic evolution. Interspersed between these clusters are regions of relative emptiness, voids that accentuate the density of the plane itself, highlighting the structure and rhythm of galactic architecture. Nebulae are a constant presence above the plane, not only in the arms, but between them as well, faint or bright depending on their composition and proximity. Ionized hydrogen clouds glow when illuminated by nearby stars, while darker regions of dust obscure light, forming sharp contrasts against brighter backgrounds. Supernova remnants add chaotic structure, expanding shells mixing with existing gas, creating turbulence that can ripple across dozens of light years. The combination of these elements produces a layered view, young stars shining brightly in open clusters, dense molecular clouds ready to collapse, ancient stars moving through inter-arm space, and remnants of past explosions shaping the next generation of stars. Observing the Milky Way at this scale emphasizes the interplay between creation and destruction. Massive stars form quickly, live briefly, and die violently, injecting energy and material into the galaxy that affects regions far beyond their immediate location. Low-mass stars dominate the stellar population, providing stability, longevity, and a slow but persistent influence on their surroundings. Black holes, both stellar and supermassive, anchor gravitational structure, shaping orbits and influencing the distribution of matter on scales ranging from individual clusters to the entire galaxy. From a cinematic perspective, flying above the plane conveys not just the structure, but the movement. Spiral arms rotate at slightly different rates than the core, creating shear between layers. Interstellar clouds drift slowly, yet continuously, their shape molded by magnetic fields and past supernova events. Pulsars and neutron stars appear like tiny points of flashing energy, punctuating the vast backdrop of billions of static-looking stars with precise periodic signals. The motion is complex, layered, and dynamic, revealing the galaxy as a system where energy, gravity, and matter interact constantly over millions of years. The supermassive black hole Sagittarius A** remains a central focus. Its gravitational influence extends far beyond the immediate cluster of stars orbiting it, affecting the motion of gas and stars thousands of light-years away. Surrounding it, dense stellar populations move in tightly bound orbits, some approaching relativistic speeds, emitting X-rays as material spirals inward, and generating jets in occasional periods of activity. Observing the galactic center from above, through dense clouds and dust lanes, emphasizes both its dominance and its subtlety. Visually faint compared to bright arms, but critical to the underlying gravitational structure of the galaxy, interstellar clouds in the Milky Way act as both bridges and barriers, guiding the flow of matter while obscuring portions of the galaxy from direct observation. Ionized regions indicate recent star formation, while cold molecular clouds harbor the potential for future stellar births. Dust lanes create dark ribbons across spiral arms, emphasizing the three-dimensional complexity of galactic structure. These clouds, combined with the stars themselves, the remnants of supernovae, and compact objects like neutron stars and pulsars, create a layered, textured galaxy, alive with motion, radiation, and ongoing transformation. The scale of the Milky Way becomes immediately evident when moving above the plane. Billions of stars do not exist in isolation, but as part of spiral density waves, interlinked gravitationally, chemically, and dynamically. Observing the galaxy as a whole, including its center, spiral arms, star-forming regions, remnants of explosions, pulsars, and neutron stars, emphasizes the Milky Way as both a static map of location and a constantly evolving system of energy, matter, and motion, where billions of years of stellar evolution are visible in every arm, cloud, and cluster. Discuss dark matter and galactic rotation curves. From above the galactic plane, the motion of stars begins to reveal a puzzle that astronomers have been unraveling for decades. The Milky Way does not rotate the way we would expect if only the visible stars and gas contained its mass. Stars far from the center orbit at speeds far higher than the gravitational pull from known matter should allow, and those in the inner regions move more slowly than they would if mass were concentrated toward the center. This phenomenon is expressed in galactic rotation curves, plots of orbital velocity versus distance from the center. And it is one of the clearest observational signs that the galaxy is embedded within a vast, invisible structure, dark matter. Dark matter cannot be seen directly, and it does not interact with light, but its gravitational influence is undeniable. From the vantage of a spacecraft gliding above the plane, the Milky Way might appear to be a collection of luminous stars and gas clouds, but underlying that apparent order is a halo of dark matter, extending far beyond the spiral arms, massive enough to hold the galaxy together and shape its rotation. Every star's orbit, every cluster's trajectory, every interstellar cloud's motion is subtly guided by this unseen presence, making the galaxy both more massive and more mysterious than the sum of its visible components. Observations have steadily refined our understanding of this invisible structure. Instruments like the Gaia spacecraft have mapped the positions and velocities of more than 1 billion stars with unprecedented precision, revealing not only the rotation curve, but the intricate motions of stellar streams, tidal tails from disrupted clusters, and the gravitational influence of unseen mass. Flying through a simulation of these mapped stars shows them tracing arcs and curves not dictated solely by visible matter, moving as if pulled by an invisible scaffold stretching across the galaxy. Gaia's catalogue is more than a static map. It is a dynamic portrait of the Milky Way's gravitational anatomy, allowing astronomers to model the distribution of both visible stars and the underlying dark matter halo with remarkable accuracy. The interplay between dark matter and the visible galaxy is mirrored in other phenomena as well. Spiral arms themselves are density waves, concentrations of stars and gas moving through the galactic disk, but their persistence over billions of years is only possible because of the stabilizing influence of the dark matter halo. Without it, these structures would disperse over far shorter timescales, leaving the galaxy a diffuse cloud of stars rather than the coherent spirals we observe. In effect, the unseen mass is as critical to the galaxy's architecture as the luminous stars, nebulae, and clusters we can see directly. At the heart of the galaxy, Sagittarius A*, the supermassive black hole, now has been imaged in a way that confirms its presence visually rather than indirectly. The Event Horizon Telescope captured light bent around the black hole, producing a ring-shaped shadow against the glow of hot, infalling gas. Observing this image is not merely a scientific accomplishment, it is a moment of scale, placing a focal point of extreme gravity at the center of the Milky Way. From above the plane, The black hole may seem diminutive compared to the hundreds of billions of stars orbiting it, but its gravitational influence is profound. Orbits of stars in the inner parsec of the galaxy are dominated by Sagittarius A*, and simulations show how it sculpts the motions of stars in the nuclear star cluster, maintains the compactness of the central bulge, and interacts with gas streams feeding into it episodically. The combination of Gaia's mapping and the Event Horizon Telescope's imaging gives a multi-dimensional understanding of the galaxy. Gaia allows us to trace the motions of stars on vast scales, revealing the mass distribution throughout the disk and halo, while the black hole image offers direct evidence of the extreme gravitational environment at the center. Together, these observations demonstrate that the Milky Way is not simply a pattern of visible stars, but a fully realized gravitational system, where visible matter, dark matter, and central supermassive objects interact continuously. Interstellar clouds, visible as faint ribbons of gas and dust threading between the spiral arms, also respond to these gravitational effects. Dense clouds may orbit within spiral arms, stretching along tidal lines, while less dense material drifts into inter-arm regions. Observing them from above, one can see their motion in response to the galaxy's mass distribution, subtly influenced by dark matter, by local stellar clusters, and by the gravitational pull of Sagittarius A*. Supernova remnants, pulsars, and neutron stars are embedded within these clouds, moving as test particles that trace both visible and invisible forces. Cinematically, flying above the galaxy under this framework is like watching a living network of motion and mass. Stars flow along paths dictated by gravity, clouds ripple with turbulence from past explosions, and clusters orbit the center in intricate patterns. The black hole sits as a silent pivot, while dark matter defines the unseen scaffolding holding it all together. This motion is not uniform or static. The spiral arms themselves rotate at different rates than the central bulge, creating shear, compression, and extended waves of star formation. Supernova remnants flash with X-rays across space, neutron stars spin with precise rhythm, and pulsars emit beams that slice through interstellar darkness like lighthouses across an ocean of stars. Observing billions of stars from above, the eye, or instrument simulating vision, can distinguish stellar populations by age and mass, seeing how older stars dominate the central bulge, while younger stars trace the arms. Blue giants cluster in dense regions of star formation, white dwarfs accumulate in older clusters, and neutron stars and pulsars mark the aftermath of massive stars' lives. This stratification is not random. It reflects billions of years of galactic evolution, of matter cycling through formation, life, death, and return to the interstellar medium. The combination of direct imaging of the black hole, high-precision stellar mapping, and rotation curve analysis provides a narrative of the Milky Way's dynamics without ever relying on assumptions. Dark matter is inferred by motion, not by sight, but its presence is unavoidable in every orbital path. Sagittarius. A asterisk is visualized not only by its effects on nearby stars, but by light itself bending around its event horizon. Star formation, supernova remnants, pulsars, neutron stars, interstellar clouds, and spiral arms are visible evidence of matter responding to gravity on scales ranging from parsecs to tens of thousands of light years. As the galaxy is traversed from above, the scale of these interactions becomes apparent. Individual stars may seem isolated, but every orbit, every cloud, every remnant is a participant in a larger gravitational dance. Dark matter dominates the unseen framework, guiding motion. The supermassive black hole anchors the center. Interstellar clouds provide the raw material for future generations. And energetic objects like pulsars, neutron stars, and supernova remnants mark the cycles of birth and death. This is a system in constant motion, billions of stars interacting over millions of years, yet moving in patterns that can now be mapped and predicted with precision instruments. The Milky Way, viewed from this perspective, is both familiar and alien. The familiar part is the overall shape, the spirals, the dense center, and the plane of stars that we recognize even from Earth. The alien aspect comes from understanding the scale, the density of objects, the presence of unseen mass-controlling motion, and the energetic processes ongoing everywhere from the galactic center to the outer arms. The combination of observations, Gaia mapping billions of stars, Event Horizon Telescope imaging the black hole, and rotation curves revealing dark matter, turns the galaxy from a vague idea into a measurable dynamic entity with structure, motion, and history, flying above the Milky Way's plane, moving past spiral arms, through interstellar clouds, observing billions of stars, and noting supernova remnants and pulsars. One sees the galaxy as a network of energy and matter orchestrated by gravity. It is a living, moving system where every component, from visible stars to the unseen dark matter halo to the supermassive black hole at the center, interacts continuously, producing patterns of rotation, waves of star formation, and zones of energetic activity that define the Milky Way at a galactic scale. Level 10. Intergalactic space between galaxies. Leaving the Milky Way behind, the familiar spiral arms fade, the central bulge dims, and stars no longer crowd the field of view. What remains is a vast, almost empty expanse, the territory of intergalactic space. Distances here stretch incomprehensibly, millions of light-years separating the nearest galaxies, each a self-contained island of stars, gas, and dark matter. In this void, the concept of distance changes from kilometers or astronomical units to megaparsecs, and even light, moving at its maximum speed, takes years, decades, or millennia to traverse the gaps. The emptiness is deceptive. Though sparse, intergalactic space is not completely devoid of matter. It contains tenuous clouds of hydrogen and helium, scattered particles, cosmic rays, and the faint gravitational influence of galaxies and galaxy clusters, subtle yet persistent forces shaping the motion of all visible objects. The local group of galaxies is the first structure encountered in this intergalactic expanse. It is a loose assembly of more than 50 galaxies, bound together by gravity, moving slowly relative to one another, yet separated by vast tracts of near vacuum. The Milky Way is one of the largest members of this group, paired with the Andromeda Galaxy, a massive spiral that dominates the opposite side of the local group. Between these giants, smaller galaxies, such as the Triangulum Galaxy and dozens of dwarf galaxies, move along trajectories defined by the gravitational pull of their larger companions. Mapping these motions has revealed a complex gravitational network, with tidal interactions subtly stretching and pulling smaller galaxies over millions of years. The Andromeda Galaxy looms as a spiral rival to the Milky Way, comparable in mass and structure, but located approximately 2.5 million light-years away. From a cinematic perspective, approaching it slowly reveals a disk of stars, interstellar clouds, and spiral arms twisting gracefully, each arm dotted with star clusters, nebulae, and remnants of past stellar explosions. Its galactic core glows faintly, home to a supermassive black hole, and the surrounding halo contains older stars and globular clusters tracing ancient orbits. The Triangulum Galaxy, smaller yet still significant, presents a different morphology, a less densely packed spiral, rich in star-forming regions, and surrounded by diffuse gas clouds that hint at previous interactions with Andromeda and other local group members. Both galaxies, along with the Milky Way, define a gravitational neighborhood in which smaller satellite galaxies orbit and interact, exchanging matter and subtly influencing each other's evolution. Moving through the intergalactic medium, the vast emptiness is punctuated by occasional faint galaxies, often dwarf ellipticals or irregulars, their stars barely visible without sensitive instruments. These isolated systems drift slowly, tracing paths determined by the combined gravitational effects of the local group's massive members. Their motion is almost imperceptible on human timescales, yet over millions of years, these orbits bring them close enough for tidal forces to stretch them, pulling stars into streams that eventually merge into the halos of larger galaxies. Intergalactic space is not static, despite appearances. Every object, no matter how small, is influenced by gravity, moving along trajectories dictated by the combined mass of all nearby galaxies and the underlying presence of dark matter. The space between galaxies contains extremely low-density gas, primarily hydrogen and helium, remnants of the early universe, dispersed by gravitational forces and past galactic interactions. These intergalactic clouds are so tenuous that a cubic meter might contain a single atom or fewer, yet they play a crucial role in galactic evolution, acting as reservoirs of material that can be accreted onto galaxies over time. Occasionally, streams of this gas are visible, pulled from galactic disks by tidal interactions, forming bridges between galaxies or trailing tails that stretch for thousands of light-years. Observing these structures provides insight into the ongoing exchange of matter between galaxies, revealing the interconnectedness of systems that appear isolated when viewed superficially. Famous galaxies, beyond Andromeda and Triangulum, punctuate the local group with distinctive features. Each galaxy carries a record of its formation history: spiral arms tracing the motion of younger stars, elliptical forms indicating mergers and dynamical relaxation, irregular shapes hinting at past interactions or tidal disruption. While Andromeda and the Milky Way dominate in mass and luminosity, the smaller galaxies are equally important, serving as laboratories for understanding star formation under different gravitational and environmental conditions. Even the faintest satellites provide clues about the distribution of dark matter within the group, because their orbits and interactions respond to gravitational forces invisible to direct observation. Distances in intergalactic space redefine scale. Traveling 1 million light-years between galaxies, stars appear not as neighboring points but as isolated islands, and clusters of galaxies only become apparent when mapped in 3 dimensions. Within the local group, these separations are comparatively small, but when moving beyond to clusters like the Virgo or Coma clusters, the scale grows exponentially, stretching across tens of millions of light-years. Within this immense void, even the brightest galaxies are separated by near vacuum, their light weakening with distance, creating a cosmic landscape of dim islands against the black backdrop. Approaching Andromeda from intergalactic space, the perspective shifts. Its halo of stars becomes visible first, diffuse and spread across hundreds of thousands of light-years, punctuated by denser regions of globular clusters. Its spiral arms appear gradually, luminous threads of young stars and star-forming regions winding outward from the dense core. The galaxy rotates slowly, yet its motion through space is measurable. Approaching it reveals proper motion, caused by the mutual gravitational pull between Andromeda and the Milky Way, a motion that will culminate in a collision billions of years from now. The Triangulum galaxy, smaller and faster in relative motion, demonstrates how interactions shape morphology, its spiral structure showing distortions from past gravitational encounters. Intergalactic space is largely invisible except through the faint light of galaxies, but instruments reveal the presence of hot gas permeating the void. This diffuse medium, heated to millions of degrees, emits X-rays detectable across vast distances and traces the gravitational wells created by groups and clusters. Even where no galaxies are directly visible, this intergalactic gas outlines the structure of the local group, tracing filaments and voids that define the scaffolding of cosmic structure. Flying through these regions gives a sense of motion, of gas streaming along filaments, of energy and matter slowly redistributing over millions of years, shaping future galactic evolution. Gravitational interactions define the trajectories of galaxies within the local group. Smaller satellites orbit the larger Milky Way and Andromeda systems, their paths elongated or perturbed by tidal forces. Streams of stars and gas extend from these satellites, forming visible evidence of disruption, while the primary galaxies accumulate this material into their halos, slowly growing in mass. These interactions, though slow and subtle, are ongoing, and the local group is a dynamic system in which every galaxy, from massive spirals to faint dwarf spheroidals, participates. Flying across this expanse, one observes a variety of galaxy types. Spiral galaxies dominate, with arms filled with gas, dust, and ongoing star formation. Elliptical galaxies are denser, more evolved, containing older stellar populations and less interstellar gas. Irregular galaxies appear chaotic, shaped by past interactions or incomplete formation processes. Each galaxy, though separated by millions of light years, reveals a story of formation, interaction, and ongoing evolution, connected subtly through gravity and the tenuous intergalactic medium that threads between them. The vastness of intergalactic space highlights the isolation of individual galaxies, yet it also emphasizes their connections. The Milky Way, Andromeda, Triangulum, and their satellite systems are part of a gravitational network, a structure that defines local dynamics, galactic evolution, and future interactions. Gas, stars, and dark matter move along paths dictated by the mass of these galaxies, subtly influencing each other over millions of years. Observing this from a cinematic perspective, flying past galaxies and through the near vacuum, gives a sense of the immense distances, the slow motion of cosmic systems, and the delicate balance of forces that shape entire clusters. The cosmic voids and filaments. The first thing that hits when leaving the Milky Way behind is how empty everything suddenly feels. Space is no longer filled with the dense crowding of stars in the spiral arms, no longer glowing with the soft haze of interstellar clouds, no longer shaped by the gravitational pull of the galactic plane. Instead, you enter the vast emptiness of intergalactic space, a region dominated not by light, but by absence, where distances stretch millions of light years and every visible galaxy becomes a distant, isolated island. Flying through this space, the mind or the instruments recording it struggles to grasp scale. Galaxies appear as tiny pinpricks of light, some barely resolvable, clustered faintly, scattered across black voids so immense that even light itself takes millennia to traverse the gaps between them. This is cosmic emptiness, but it is not uniform. It is structured, shaped by gravity into filaments, vast strands of galaxies threading through emptiness, and cosmic voids, enormous regions almost entirely devoid of matter. These filaments are the backbone of intergalactic structure. They are not obvious when viewed from Earth, but traveling along them reveals their true nature. Galaxies aligned along strands of invisible mass, connected through gravity and sometimes tenuous clouds of hydrogen and helium gas. The filaments stretch for tens of millions of light years, connecting clusters and groups of galaxies in networks that resemble a cosmic web. Within the filaments, gravity gently guides galaxies along paths that will eventually lead to encounters, mergers, and interactions over billions of years. Each galaxy is not isolated, but part of this network, moving slowly along invisible highways, sometimes colliding, sometimes merely brushing past one another, leaving trails of stars and gas in their wake. Cosmic voids dominate the space between filaments. These are enormous dark regions, hundreds of millions of light years across, where almost no galaxies exist. Flying through a void is a strange experience. The emptiness is profound, broken only by the faint glow of the occasional dwarf galaxy or an isolated spiral far in the distance. The darkness feels absolute compared to the crowded stellar neighborhoods within galaxies. Even the glow of the Milky Way and Andromeda diminishes as distance grows, until the two giants themselves shrink to faint points of light. Floating here, the scale of the universe becomes undeniable. Distances are so vast that galaxies that seem near are in reality separated by millions of years of light travel, and any motion, even at thousands of kilometers per second, requires millions of years to produce significant displacement. The local group emerges as a faint cluster within this web, a gravitational neighborhood in the emptiness. The Milky Way and Andromeda dominate, each a massive spiral shining faintly in the blackness, while the smaller Triangulum galaxy orbits Andromeda like a companion tugged by gravity. Dwarf galaxies pepper the space around these giants, some barely detectable, their stars sparsely scattered, revealed only in sensitive surveys of the local universe. Recent discoveries have highlighted how many of these faint systems exist, invisible to early telescopes but now catalogued thanks to deep imaging campaigns. Each dwarf galaxy carries clues about galaxy formation, tidal interactions, and the invisible gravitational forces sculpting their motion. Flying toward Andromeda from intergalactic space gives a cinematic view unlike anything inside a galaxy. First comes the halo, a faint diffuse glow of old stars spread across hundreds of thousands of light years. Within it, streams of stars arch outward, remnants of past mergers with smaller satellites. Moving closer, the spiral arms appear, twisting outward in luminous lanes dotted with star-forming regions, nebulae, and compact clusters. Andromeda rotates slowly, its motion subtle but measurable against the black backdrop of void. Yet it is moving inexorably toward the Milky Way, a collision predicted to occur in roughly 4.5 billion years. Approaching this encounter visually, the two galaxies remain tiny, distant islands of light in the vast emptiness, but their mutual attraction is strong, already shaping their paths long before any stars or gas clouds will interact. Triangulum, smaller and less massive, presents a different portrait. Its spiral arms are thinner, less tightly wound, but filled with active star-forming regions, gas clouds, and bright clusters. Triangulum's orbit within the local group positions it as a secondary participant, subtly influenced by Andromeda's gravity and the collective pull of smaller satellites. Observing Triangulum from the perspective of intergalactic space emphasizes its isolation relative to Andromeda and the Milky Way, yet it remains connected through the invisible forces that structure the local group. The emptiness of intergalactic space is deceptive because it contains faint matter. Hot, diffuse gas threads through voids and filaments, nearly invisible but detectable with X-ray telescopes. This gas contributes to the mass of the local group, helps trace filamentary structures, and slowly moves under gravitational forces. Streams of hydrogen and helium link galaxies across millions of light years, feeding future growth or slowly accreting onto galaxies over cosmic time. Even in regions that appear completely empty, this tenuous material marks the skeleton of intergalactic structure, flowing silently along filaments or stretching into voids, almost imperceptible, yet essential for understanding the distribution of mass in the universe. Floating through this space provides a cinematic contrast. Voids stretch endlessly, the blackness broken only by sparse, faint galaxies. Filaments appear as linear clusters, dense enough to show structure, but tenuous compared to the crowded interior of a galaxy. Andromeda and the Milky Way, still millions of light-years apart, grow slightly in size as perspective shifts. Triangulum glides alongside Andromeda, orbiting its gravity. Dwarf galaxies blink faintly into view, revealing themselves only through careful observation. Moving slowly, the view emphasizes distance, isolation, and scale. Each galaxy is self-contained, yet connected, a luminous island drifting through near-perfect darkness, part of a web that cannot be seen with the naked eye, but that defines the dynamics of the local universe. The predicted Milky Way-Andromeda collision adds tension to this emptiness. While billions of years away, the mutual gravitational pull is already measurable, causing a subtle approach visible only through precise mapping of velocities and positions. Stars within each galaxy are too far apart to collide directly, yet the galaxies themselves will merge, tidal forces stretching arms, clouds of gas interacting violently, and star formation surging in compressed regions. Observing them from intergalactic space, even today, shows two islands of light slowly drawing together against a backdrop of near-perfect void, a reminder of the slow-motion drama of cosmic timescales. Dwarf galaxies are scattered throughout this environment, often orbiting the larger members of the local group, but sometimes isolated in the void. Recent surveys continue to discover these faint systems, previously invisible, each contributing to our understanding of galactic formation and evolution. Their presence highlights that even in intergalactic space, small-scale structures exist, tracing the influence of gravity far from the luminous centers of massive spirals. Streams of stars from disrupted dwarfs stretch between galaxies, evidence of past interactions and ongoing evolution. Cinematic fly-throughs of intergalactic space emphasize the emptiness and scale. Passing through voids, galaxies appear as tiny islands, isolated and glowing faintly against the darkness. Filaments stretch for millions of light-years, aligning clusters in subtle strands that hint at the invisible gravitational network shaping the universe. Hydrogen clouds drift, barely detectable, illuminated only when gas interacts with cosmic rays or the light of distant galaxies. Moving closer to Andromeda, Triangulum and the dwarfs, details emerge. Halos of stars, twisted spiral arms, globular clusters, faint streams, and distant supernova remnants. Each object is a marker of the dynamics of gravity, history, and cosmic structure, small lights within a vast dark sea. Intergalactic space, despite appearing empty, is alive with motion. Galaxies orbit one another, streams of gas and stars trace past interactions, filaments guide the flow of matter, and voids provide the canvas upon which the structure of the universe is painted. Every galaxy in the local group participates, whether massive or faint, spiraling, elliptical or irregular. Each interacts gravitationally, sometimes merging, sometimes passing in slow flybys, with subtle exchanges of matter and energy, all occurring across distances that dwarf the scale of the Milky Way. Level 11. The Cosmic Web. Large-scale universe structure. Moving beyond the local group, the universe expands into an intricate network, the cosmic web, a vast architecture of matter stretching across hundreds of millions of light-years. Galaxies no longer appear as isolated islands drifting through emptiness. They are concentrated along filaments, strands of gravitationally bound matter, connecting clusters and superclusters, threading through enormous voids that appear almost entirely empty. Observing this web, the scale of the universe becomes tangible. Entire clusters of galaxies shine faintly along these filaments, while voids, stretching tens to hundreds of millions of light-years, separate them like dark seas. Flying along a filament connecting two galaxy clusters, the perspective reveals both the density of galactic structures and the emptiness of the surrounding space, showing a universe organized on the largest scales imaginable. Clusters of galaxies are the nodes of this web, each containing hundreds or even thousands of galaxies bound together by gravity, their motions tracing the invisible pull of dark matter. Within these clusters, individual galaxies swirl in orbits dictated by the cluster's total mass, not just the luminous matter that can be observed. Hot intra-cluster gas fills the space between galaxies, heated to millions of degrees, glowing in X-rays, and providing a luminous medium that maps the structure of clusters. From a cinematic perspective, flying through a cluster is like moving through a luminous cloud of stars on a galactic scale. Dense pockets of galaxies embedded in a sea of invisible gravitational scaffolding, all connected to neighboring clusters by filaments of matter. Superclusters expand this structure further, tying together multiple clusters across hundreds of millions of light-years. The Virgo supercluster, containing the Milky Way, demonstrates how these immense structures create the scaffolding of the universe, with clusters of clusters forming along filaments and separated by enormous voids. From above, the cosmic web begins to appear as a lattice of light and darkness, filaments stretching endlessly, linking dense nodes of galaxies, while voids provide the background canvas of near-perfect blackness. The scale is difficult to comprehend. Individual galaxies are invisible at this distance, appearing as faint smudges, yet their combined mass and gravity dictate the motion of the larger structures, guiding the flow of matter along the cosmic filaments. Mapping this cosmic web relies on multiple techniques. Gravitational lensing allows astronomers to see the influence of dark matter, which bends light from distant galaxies. Observing arcs of distorted light across the sky, researchers can trace the distribution of mass, including the invisible dark matter that forms the backbone of the web. Filaments become apparent in these lensing maps, revealing strands connecting clusters and superclusters, structures that guide the formation and evolution of galaxies over billions of years. Flying along these filaments, one can visualize the unseen mass, tracing invisible highways where galaxies drift along paths determined by the total gravitational potential. The cosmic microwave background, CMB, provides a complementary perspective, a relic radiation field left over from the early universe, appearing as a faint, uniform glow across the entire sky. Tiny fluctuations in the CMB correspond to the seeds of the cosmic web, regions of slightly higher or lower density that over billions of years evolved into the filaments, clusters, and voids we observe today. Flying through this structure cinematically, the CMB can be imagined as a diffuse light filling intergalactic space, subtle patterns hinting at the early gravitational perturbations that grew into galaxies and clusters. These tiny variations, measured with incredible precision by missions such as Planck and WMAP, provide a blueprint for the universe's large-scale structure, showing the initial conditions that shaped the cosmic web. Filaments themselves are not just collections of galaxies. They contain dark matter, intergalactic gas, and small dwarf galaxies, flowing along the gravitational potential wells created by the mass of the clusters at their ends. The density along filaments is higher than in voids, yet far lower than in galaxy clusters. Traveling along a filament in a cinematic fly-through, galaxies appear sporadically, sometimes aligned along the central axis of the filament, sometimes in small groups. Gas clouds, invisible to optical telescopes, can be inferred through X-ray and radio observations, drifting along the filament like cosmic rivers connecting the dense nodes at either end. Voids provide contrast to this structure, vast regions where few galaxies reside, their size dwarfing even the largest clusters. Within voids, matter density is extremely low, with only isolated galaxies or small groups, often faint dwarfs, barely detectable with modern instruments. These voids influence the motion of galaxies at their edges, with filaments and clusters effectively pulling matter out of the emptiness, creating flows of galaxies moving along the cosmic web. Flying through a void, the emptiness is profound, punctuated only by distant points of light representing isolated galaxies, reinforcing the sense of scale and isolation. Clusters, filaments, and voids together form the skeleton of the universe, a structure that defines how matter is distributed and how galaxies evolve. Galaxies in dense nodes experience more interactions, mergers, and tidal stripping than those in filaments, while galaxies in filaments experience steady infall toward clusters, and those in voids evolve in relative isolation. Observing this structure provides insight into galactic evolution, showing how environment shapes star formation rates, galaxy morphology, and gas content over billions of years. From a cinematic perspective, one can visualize galaxies drifting along invisible highways of dark matter, colliding occasionally at cluster nodes, and stretching long tidal tails along filaments connecting multiple clusters. The flow of matter along filaments is subtle but continuous. Dark matter dominates the gravitational potential, guiding the movement of galaxies and gas along predictable trajectories. Gas streams trace these flows, occasionally compressing to trigger star formation or feeding the growth of clusters. The combination of gravitational lensing, CMB maps, and galaxy surveys reveals the complex network of filaments and nodes, allowing a three-dimensional visualization of the cosmic web. Flying through these structures, one observes the density contrast. Dense clusters glowing faintly with thousands of galaxies, thin filaments dotted with smaller systems, and vast voids stretching beyond view, a dynamic and organized structure emerging from the apparent emptiness. Cosmic filaments connect clusters like superhighways, and at intersections, massive nodes form where clusters and superclusters meet. These nodes often host the largest galaxies in the universe, including central giant ellipticals, whose mass dominates local gravitational potentials. Surrounding these central galaxies, hot gas and satellite systems trace the dark matter halo, forming luminous and X-ray emitting structures that highlight the gravitational dynamics at play. Flying along a filament toward such a node, one sees galaxies accelerating subtly, gas streams converging, and the density increasing as the cluster core approaches. The cosmic microwave background links this structure to the universe's origin. Tiny fluctuations in temperature and density, visible as slight color variations in the CMB, correspond to the primordial seeds that evolved into the cosmic web. Following a filament from its cluster node back through space and time, one can trace the growth of structure, observing how small perturbations in the early universe amplified under gravity, forming the intricate lattice of matter that dominates the observable cosmos today. Cinematically, one can imagine flying backward, seeing galaxies shrink, filaments thin, and voids grow, visualizing the evolution of the cosmic web from the uniformity of the CMB to the complex network we see now. Dark matter, though invisible, is the framework upon which this entire structure rests. Without it, filaments would not form, clusters would not accumulate mass, and the universe's large-scale structure would appear diffuse and unorganized. Gravitational lensing allows a glimpse of this invisible web, bending light from background galaxies, producing arcs and distortions that trace the mass distribution along filaments and across clusters. Observing these distortions from a cinematic viewpoint gives the sense of moving through an unseen structure, where gravity shapes the movement of all visible matter. Galaxy surveys reveal even more subtle details. Faint dwarf galaxies trace the periphery of clusters and filaments, often elongated along gravitational gradients, evidence of tidal interactions and dark matter influence. Streams of stars stripped from disrupted dwarfs form filaments themselves, invisible to optical telescopes without careful mapping, yet part of the intricate cosmic web. Flying through a filament in such detail, these faint structures appear as ghostly threads of light, tracing the invisible forces shaping the universe. Gravitational waves from merging black holes in clusters. The universe on its largest scales is not silent. Across the cosmic web, the vast interconnected network of galaxy clusters and turbulent dark filaments strung across unfathomable distances. New discoveries are expanding our understanding of how structure grows, evolves, and even vibrates with energy not seen by human eyes until only recently. Telescopes both on the ground and in space are now mapping cosmic voids with unprecedented clarity. These enormous regions, vast expanses tens to hundreds of millions of light-years across, where few galaxies dwell, were once mere mathematical predictions, the negative spaces between clusters of matter. Over the last decade, galaxy surveys such as the Sloan Digital Sky Survey, SDSS, DESI, Dark Energy Spectroscopic Instrument, and the Euclid mission have traced these voids in 3 dimensions, revealing their shapes, sizes, and complicated boundaries where filaments pinch off or merge. These voids are not empty spheres. They are sculpted by gravity over billions of years, the result of matter collapsing into filaments and nodes, leaving behind giant bubbles of low-density space that widen and deepen as the universe expands. News from these surveys continually reshapes our mental map of the cosmic web. Astronomers announce the discovery of massive galaxy clusters that defy traditional expectations of structure formation, clusters so large and so early in the universe's history that their existence challenges previous models of gravity and matter distribution. Some clusters, detected billions of light-years away, contain thousands of galaxies packed into regions just a few million light-years across. These early giants suggest that the seeds of the cosmic web grew faster and clumped more efficiently than expected, possibly hinting at unknown physics in the interplay between dark matter and normal matter in the infant universe. Visualizing one of these clusters is like flying into a galactic metropolis. Imagine approaching a city from above, but instead of highways, you see lines of galaxies streaming toward a dense core, drawn inexorably inward by gravity. At the center, dozens of massive elliptical galaxies, themselves the remnants of countless mergers, glow with concentrated light, while surrounding spirals and dwarfs orbit in chaotic but predictable paths. Between them, hot gas heated to millions of degrees radiates in X-rays, a luminous fog that betrays the cluster's gravitational pull. This hot intra-cluster medium is one of the clearest signals of a true cluster, a cauldron of violent motion and heated plasma, Even more intriguing are the patterns revealed when void mapping is combined with cluster discovery. These voids are no longer simple bubbles punched out between concentrations of galaxies. They are complex, irregular regions with filaments bending and twisting around their edges. In some areas, voids appear intertwined, like a chain of empty caves lining the dark corridors between cosmic highways. Researchers now refer to supervoids, especially large regions hundreds of millions of light-years across, where galaxy density drops sharply, and they are finding that these structures influence the motion of galaxies at their edges, pushing matter into filaments and toward clusters. Flying through one of these supervoids in a cinematic visualization, the viewer would witness an eerie quiet, a dark expanse where light from galaxies is faint and scattered, where gravitational interactions are minimal, and where the cosmic microwave background appears subtly altered due to the integrated Sachs-Wolf effect, a signature left on the oldest light by the presence of large gravitational potential wells and voids. These signatures are part of how astronomers detect and confirm void structures that, to the eye, are invisible in isolation. Another frontier of modern cosmic web science comes not from light at all, but from ripples in space-time itself, gravitational waves. These tiny distortions in the fabric of the universe were first directly detected in 2015 by LIGO when two stellar mass black holes spiraled together and merged, sending out waves that stretched and shrank space by less than a proton's width as they passed through Earth. Since then, dozens of similar events have been recorded from black holes and neutron stars merging. But clusters of galaxies add an entirely different dimension. Galaxy clusters, because of their density and the large populations of massive stars and black holes they contain, are breeding grounds for powerful gravitational wave events. Within a cluster, stars evolve, explode, and leave behind compact remnants, neutron stars and black holes, often in close proximity. Over time, through interactions and gravitational nudges, pairs of these compact objects can form tight binaries. As these binaries spiral closer together, they emit gravitational waves that grow stronger and eventually peak in a colossal merger event. These mergers are not confined to single star systems, but occur most frequently in the dynamic environment of a cluster. Sometimes two black holes deep inside a cluster will interact with others, exchanging momentum, tightening or loosening their orbits in a complex gravitational dance before finally coalescing. The population of merging black holes detected so far suggests that a significant fraction of them come from dense stellar environments, star clusters, and the cores of galaxies, including those inside massive galaxy clusters. This shift in understanding emerged only in recent years as gravitational wave detectors expanded sensitivity. The pattern and frequency of these signals contain information about where they come from, and clusters, with their high density and frequent dynamical interactions, are now recognized as major contributors to the gravitational wave background. Future detectors like LISA, Laser Interferometer Space Antenna, which will operate in space and be sensitive to lower frequency waves, are expected to detect mergers from even more massive systems, including intermediate mass black holes that may form in cluster cores. Cinematic visualizations of these events place the viewer deep within a cluster, surrounded by billions of stars and hundreds of galaxies. Somewhere unseen, hidden by dust and light, two black holes orbit each other, closing in slowly over millions of years, their final moments silent until the space-time around them begins to vibrate. These waves radiate outward, stretching and squeezing the cosmic web itself, passing through filaments and voids alike, carrying with them the signature of the violent astrophysical processes that birthed them. The cosmic web's filaments are not merely bridges of galaxies. They are highways along which gas flows, feeding the growth of clusters. Streams of hydrogen and helium, originally part of the primordial soup that filled the early universe, still travel along these filamentary paths. Modern observations using the Sunyaev-Zeldovich effect, the interaction between cosmic microwave background photons and high-energy electrons in hot gas, are beginning to reveal these streams directly, allowing astronomers to map gas flows between clusters with increasing resolution. These structures are estimated to contain a significant fraction of the missing baryons, the normal matter that accounts for everything we see in stars and planets, but which has been difficult to locate observationally. Mapping these gaseous filaments alongside voids and clusters brings the cosmic web into sharp relief. Imagine a three-dimensional lattice where each filament pulses faintly with the glow of intergalactic gas, connecting luminous nodes of galaxy clusters like cables supporting a vast multidimensional net. Between these cables lie immense empty spaces, voids, stretching so deep and so dark that not even the dim glow of gas can reach them. Yet even these voids have structure. Veils of the cosmic microwave background that have been subtly imprinted by the universe's expansion and the gravitational influence of vast clumps of matter nearby. Recent surveys have identified not just filaments and voids, but superclusters, the next level of organization in the cosmic web, linking multiple clusters over distances of hundreds of millions of light-years. One of the largest known is the Laniakea supercluster, the region of space that contains the Milky Way. It spans more than 500 million light-years and contains tens of thousands of galaxies. Laniakea's identity as a supercluster comes not from a single, coherent structure, but from how galaxies and matter flow through space under gravity's influence, converging towards certain attractor points in the universe's large-scale structure. The discovery and mapping of these massive structures depend heavily on cutting-edge technology, multi-object spectrographs that measure galaxy positions and velocities across huge swaths of sky, radio telescopes that track intergalactic gas, X-ray satellites that observe hot cluster gas, gravitational wave detectors that listen to space-time itself. Each dataset adds a layer of information to the cosmic map, showing where matter is, where it flows, and how it changes over time. Deep wide-field sky surveys have also revealed faint galaxies in the local universe that sit far outside rich clusters or dense filamentary regions. These galaxies are difficult to detect because they are low in luminosity and often free of bright young stars. Some are gas-rich dwarfs that never experienced the intense interactions seen in cluster environments, while others may be relics of early galaxy formation, largely untouched for billions of years. Finding and cataloging these faint systems helps astronomers understand how environment influences galaxy evolution and how widespread dark matter must be to sustain such isolated systems. Visualizing the cosmic web in a cinematic fly-through, one would see strands of galaxies streaming along filaments like luminescent threads in an enormous three-dimensional tapestry. Clusters appear as bright knots studded with thousands of galaxies, surrounded by halos of hot X-ray emitting gas. Between these strands lie immense dark regions where few stars sparkle. Gravitational lensing, the bending of light by massive structures, reveals the invisible component of the web, dark matter. Lens-induced arcs of distant galaxies traced around cluster cores light up maps of mass distribution that do not match visible matter alone. These maps show vast halos of dark matter enveloping clusters and extending outward along filaments, making the cosmic web not just visible but quantifiable. Each gravitational wave signal adds another layer of richness to this picture. As black holes merge in distant clusters, their waves propagate through the universe, passing through filaments, voids, and galaxy superclusters alike. These ripples carry information not just about the merging objects, but about the space they travel through. Subtle distortions that could one day be used to probe the cosmic web itself, revealing hidden structure in the gaps between galaxies. This interplay of matter, motion, gravity, gas, light, and gravitational waves makes the cosmic web the most dynamic structure in the universe. It is not static. It evolves continually as gravity draws matter into denser and denser configurations, as gas flows feed clusters and star formation, and as dark matter molds the shape of space on the largest scales. The news headlines: massive cluster discoveries, deeper void maps, gravitational wave detections from merging black holes are not isolated events, but pieces of a larger story of cosmic evolution. a story written across billions of years and billions of light-years of space. Level 12. The edge of the observable universe. Dawn of time. The universe stretches farther than the mind can immediately grasp. From Earth, we can see only a fraction of the whole, the observable universe, limited by the speed of light and the time since the Big Bang. Its boundary, the cosmic horizon, lies roughly 46 billion light-years away, a distant wall where the earliest light we can detect still travels toward us across the expanding cosmos. Beyond it, space continues, but any signal from there will never reach Earth. Crossing the threshold of the observable universe is not just a journey across distance, it is a journey backward in time, moving toward the moments when the universe was newborn, a dense, hot, expanding sea of energy waiting to form the first structures. At this horizon, space is almost unrecognizable. Galaxies are tiny flickers, and time itself seems compressed. Every photon, an ancient messenger from a past that existed when the universe was only a fraction of its current age. The earliest galaxies, forming perhaps 200–400 million years after the Big Bang, are compact, intensely luminous, and chaotic. They burn hot, dominated by massive, short-lived stars that seed the universe with the first heavy elements. These proto-galaxies are different from the spirals and ellipticals familiar in the local universe. Their structures are irregular, clumpy, and turbulent, reflecting the raw energy and density of their formation. Recent observations have transformed our understanding of this era. The James Webb Space Telescope has imaged galaxies so distant that their light traveled over 13 billion years to reach us. Some of these galaxies formed just 300 million years after the Big Bang, shining faintly in the infrared after their starlight stretched by cosmic expansion. Each detection is a window into the infancy of the universe, revealing structures smaller and denser than the massive spirals seen today, yet already forming stars at incredible rates. These earliest galaxies are building blocks, merging and interacting under gravity, eventually evolving into the complex galactic structures that populate the universe we see now. The first stars, known as population 3 stars, are equally extraordinary. Composed almost entirely of hydrogen and helium, they ignited without the heavy elements forged in previous generations, burning hotter and faster, some reaching hundreds of times the mass of the Sun. Their lives were brief but transformative. As they exploded in supernovae, they seeded the surrounding gas with heavier elements, enabling the formation of subsequent generations of stars, planets, and eventually the material that would make life possible. Observing these early stars directly remains a challenge, but their fingerprints are visible in the chemical composition of later galaxies and in the faint glow of the early universe, captured by telescopes like Webb. Alongside these early galaxies, the primordial quasars stand out as cosmic lighthouses. Supermassive black holes forming just a few 100 million years after the Big Bang appear as intensely bright points of light, fueled by gas accretion that emits tremendous energy. The existence of such massive black holes so early challenges models of galaxy and black hole formation, suggesting that some regions of the early universe condensed far faster than previously imagined. These quasars illuminate the intergalactic medium around them, carving ionized bubbles through the neutral hydrogen that filled the early cosmos, marking the epoch of reionization, a transformative period when light began to dominate darkness on cosmic scales. The very fabric of space was itself changing. Cosmic inflation, a brief but violent expansion in the first tiny fraction of a second, stretched the universe by factors beyond comprehension. This rapid expansion smoothed the universe, distributing matter and energy almost uniformly, yet quantum fluctuations became the seeds of the cosmic web, the galaxies, filaments and clusters that would emerge billions of years later. Observing the universe at its earliest stages is like peering at a blueprint, a faint imprint of fluctuations frozen into the cosmic microwave background, revealing the initial conditions that shape the evolution of all structure. Flying through this era, the visual experience is surreal. Light from early galaxies, stretched into the infrared by the expansion of space, glows faintly, scattered across the vast darkness. Dense clouds of hydrogen and helium drift between galaxies, opaque in some regions, transparent in others, forming filaments that hint at the beginnings of large-scale structure. Primordial quasars punctuate the darkness with sharp brightness, beacons marking areas of accelerated formation and gravitational collapse. The universe is both empty and violent, quiet in the vast distances, yet energetic in the bursts of light and star formation that define the cosmic dawn. Dark energy, subtle yet dominant, is already shaping the expansion. Even at these early epochs, space is stretching, carrying galaxies away from each other at accelerating speeds. Light traveling across these distances is stretched further, its wavelength elongated, revealing the deep infrared signals that Webb and other telescopes now capture. The accelerating expansion defines the observable horizon itself, setting limits on what any observer can ever see. Beyond this boundary, the universe continues, but its light cannot reach us, leaving humanity forever confined to this expanding bubble of observation. The discoveries at the edge of the observable universe are constant and evolving. Every new deep-field survey uncovers galaxies fainter and further than the last, pushing the horizon slightly farther, revealing more about the first billion years of cosmic history. The combination of early galaxy formation, massive black holes, the epoch of reionization, and the lingering glow of cosmic inflation paints a picture of a universe brimming with energy, structure, and potential, yet still dominated by forces and phenomena largely invisible and unexplained. Imagining the flight along this edge is awe-inspiring. Faint galaxies drift across the field of view, ancient light stretching across time. Massive quasars blaze in contrast, illuminating the surrounding medium. The first stars burn hot and die quickly, leaving the universe increasingly complex. Intergalactic filaments begin to emerge, foreshadowing the intricate cosmic web billions of years later. Dark energy subtly shapes the space between these objects, accelerating expansion and defining the cosmic horizon, the ultimate boundary for any observer. Humanity's gaze from Earth, or from telescopes like Webb, is the first step toward understanding this remote frontier. Even as we measure and image the earliest galaxies, every observation is filtered through billions of years of cosmic expansion, revealing light that left its source before Earth even existed. These discoveries place us in perspective, small, transient observers peering at light from the infancy of time, glimpsing the mechanisms that shaped all matter, all galaxies, and all stars, including our own sun and planet. At the very edge, the universe is still forming. Gravity slowly gathers matter into the first clusters, star formation spreads, supernovae seed the intergalactic medium, and dark energy pushes galaxies apart. Observation is limited, but technological progress has allowed humanity to see farther than ever imagined, capturing light from when the cosmos was less than 5% of its current age. The birth of light, the shaping of space by dark energy, and the emergence of structure all converge in these observations, offering a window into the processes that created the universe as we know it. From this vantage, the universe is at once vast, ancient, and dynamic. The cosmic horizon represents both a limit and an invitation, defining the boundary of what we can see while hinting at what lies beyond. Humanity's place in the cosmos is tiny, yet the ability to observe and understand events from the dawn of time connects us to the universe's earliest epochs. Every photon arriving from the edge of the observable universe carries information about processes billions of years ago, illuminating not only distant galaxies, but the forces and physics that shaped everything, including the space we inhabit today. Looking at the earliest galaxies, the first stars, and primordial quasars, the cinematic vision becomes profound. Faint clusters of light across an endless expanse, intergalactic gas flowing between them, dark energy shaping the expansion of space itself, all pointing to a universe that is ancient, complex, and still evolving. At this edge, the limits of observation define our understanding, Yet the very act of observation places humanity as witnesses to cosmic history, capable of tracing the evolution of space and time, from the first light to the galaxies we inhabit today.